My fellow physicists, I think it's time we start. It's 1 o'clock. I'm very grateful that you're joining us in such enormous numbers, and welcome to this second all digital edition of FYSICA. And it's a very special FYSICA because the Netherlands Physical Society is now precisely 100 years and 2 weeks old. And it's an honor to be hosting this in this special time. And my name is Diederik Jekel, and I'm the chair of the Netherlands Physical Society. A few things I need to mention. I'm sure you are all much more versed in using Zoom when you compare it to last year. Back then, we all had to adjust very quickly and learn new digital skills. But we're now sort of Teams or WebEx or Zoom experts. It is great for speakers to see your camera and not to talk into some sort of dark void. And it's a much more friendly conferencey atmosphere when you put on your cameras. However, keep in mind that this conference will be recorded. Furthermore, please be careful in muting your microphone. From time to time, just take a look if your microphone is still muted, because it can take away the attention, like I said before, from the wonderful speakers that we have here today. And they truly are wonderful. Every year, we have a special tradition at FYSICA where we try to get last year's Nobel Prize laureates and have them speak at our conference. And for the last 13 years, we've managed to do this. And this year, not one, but 2 laureates will make an appearance and give a talk about last year's prize and the work that they did. Reinhard Genzel and Roger Penrose. We also have Daniel Bon, who will give his talk on his work on the physics of the coronavirus spread. And he's here because he's this year's FYSICA Prize winner. And we'll also hear from the 3 finalists of the Young Speakers Contest. We'll have a pub quiz, hear about the history of physics in the Netherlands and the NNV, talk about equations on walls, have all kinds of prizes, and all this in a wonderful conference ahead. It's a busy schedule, but one that is jam-packed with nice talks and inspiring fellow physicists. And you probably have questions for these physicists, and if you do, please put them in the chat and I will try to pass them along to whomever it's addressed to. We're here with hundreds of people, so this is probably the best way to make sure it will go smoothly. And it's too bad that due to time constraints, we cannot go into many questions. The pub quiz at the end will be on menti.com. We'll explain it all at the end and requires a second screen like a phone or an iPad or a laptop. And there you can fill in the answers. And in the meantime, on this Zoom, what you're watching right here, you can hear about the questions. And later on, I will make it all perfectly clear. So finally, a little bit about the Netherlands Physical Society. For those who don't know, we try to make the physics environment in the Netherlands as good as it can possibly be. That means that it's important that enough money goes to physics research, and policymakers should constantly be reminded about the importance of physics. But it also means that more young people should be inspired to take a career in physics, and we try to improve the education standards in the Netherlands and improve the number of qualified teachers. But we're also for physicists at companies and everywhere else. We try to make it more inclusive and diverse. And all these things are very important, I think, in a time where it seems that not all people understand how important science is in our everyday lives. That not all people in the Netherlands understand even the basic concepts of the scientific progress. And I hope, therefore, that if you're not yet a member, please consider becoming one. And if you're a professor and you have people in your group that are not yet a member, help them become one. We're the 3rd largest physics society in Europe, and we can only be as successful or powerful as the amount of members that we have. So now for a little bit of history. In the beginning of the 20th century, physics in the Netherlands was on a world high-class level. And in a few years, 3 Nobel Prizes for physics was awarded to Dutch scientists. In 1902 to Lorentz and Zeeman for their work on magnetism and radiation. In 1910 to Johannes Diederik van der Waals for his equation of state of gases and liquids. And in 1913 to Heike Kamerlingh-Onnes for his research on the properties of matter at low temperature, which led to the liquefaction of helium. But physics was going through some massive changes. It was the dawning time of quantum mechanics and relativity, and the classical physics picture was slowly becoming obsolete. In these years, a need for a society for physicists was growing. a place where they could meet and discuss, to communicate better about new findings. And a magazine with all new discoveries and ideas was being published. 3 of the 4 mentioned Nobel Prize laureates and a group of other physicists took initiative and started the Nederlandse Natuurkundige Vereniging. On April 2nd, 1921, during the 18th Natuur- en Geneeskundig Congress, it was founded. And about the same time, they started making the magazine, Nederlands Tijdschrift voor de Natuurkunde, which was called FYSICA back then, with Nederlands Tijdschrift voor de Natuurkunde as a subtitle. So in our archives, sharing screen, yes. In our archives, we've kept some amazing mementos from the last century, including these wonderful lists, a list of everyone present at the NNV meeting in 1921, for instance, with signatures from people like Lorentz, Van der Waals, Erefest, Ornstein, Zernike, Holst, Minnaert, and the list goes on and on and on, which makes a pretty cool list, I would say. We also have cards of physicists who want to join as a member. Dr. A.D. Fokker, for instance, and here you see a principal and a teacher who also wants to become members. And also someone by the name of Miss Offerhaus, who is registering. I don't know if fellow physicist Herman is watching and if this is a family member. But there are also many interesting letters, for instance. This is a letter from Pieter Zeeman, directed at meneer Ornstein. And he says here, "Dear esteemed Mr. Ornstein, this afternoon I was reminded that I still neglected to answer your questions regarding the founding of a physical society. I'm sympathetic to this idea, and I would like to sign off on a starting meeting, and I would like to participate in a meeting in advance to talk things through." And then it's interesting how he goes on, something that really doesn't change through the centuries with professors being very busy. I do need to add to this that in the new society, I will not be filling any governing duties, sort of exclamation points and underlined. As you know, I've just asked to be relieved of my role as the secretary of the Academie and also of a few other roles. I'd like to keep this space. As I understand from Mr. Lorentz, the Solvay conference will be held roughly at the same time as the conference in Utrecht. I need to be there as well, so I cannot make it in Utrecht. I apologize for my late response, Peter Zeeman, which is quite interesting. He had a very good reason. Because the Solvay conference was exactly at that time, and this was vital for understanding of quantum mechanics. And the third one was just precisely during the foundation of our society. So if you are still at this point watching this and thinking, well, is it cool to become a member of the NNV? Here are some forms, for instance, for Lorentz and Zeeman, who want to become a member. So if you at home think you're cooler than these 2 physicists, we should meet afterwards, and otherwise you should just become a member. And finally, minutes from the first meeting of the Netherlands Physical Society on the 23rd of April, and we see the names of Kannegieter, Holst, Burgers, Zernike, who could not make it, by the way. And a few things were discussed: how to operate a society, propaganda for new members, as they call it, which is still relevant to this day. And it tries to establish how often and where they need to meet. A very nice sentence is, "The best time to meet appears to be in the afternoon at 4 o'clock. By the way, we still tend to meet at this time. Last year it was 5 o'clock, but usually 4 o'clock. And the first meeting should be in September, and it might be nice to invite someone from abroad to speak." And it casually mentioned it might be Langmuir or Einstein. Some nice foreign guests. So these people, they started our society, and they just finished the pandemic in 1919, and we're thinking about the future of physics. This year, there are quite some similarities with this pandemic, and also about thinking about the future. We have this year wonderful centennial activities, and one of the ideas is a roadmap to the future. And for this, we need your help. You can go to the website there. It says on below, I don't know, at the end of the day or maybe tomorrow, but please do, because we need your help. We want to know from all of you when you are expecting certain breakthroughs to happen, sort of a wisdom of the crowds thing that we want to try here. So what you do is you go to this website and the pad naar de toekomst.nl, and it's also in English, and there you can fill in, you can register and you can fill in when you think that certain things are bound to happen. So you end up sort of on this timeline, and there you can see a pull-down menu of many possible things, like when will the academic language be Chinese, when will be on Mars, stuff like that. And here, for instance, I would say something about when energy from the power grid is delivered by the first commercial nuclear fusion reactor, for instance, and you could add a note. And if you don't agree with what I'm saying here, then please feel free to be invited to say something yourself and adjust how fast it goes. And it's sort of a wisdom of the crowd. So we take a look what everybody says and hopefully get a better idea of the future, what the future holds. So I would like to go on and introduce Christa Hoyer. In April 2022, my second term will end as chair of this wonderful society, and I'm very happy to tell all those who haven't heard it yet that none other than Christa Hoyer will take over the metaphorical hammer and fulfill this honorable role as president. As it is customary, she starts with a year of being vice chair, and she just started this, and together we will do different parts of today's program. So I would also like to thank Petra Rudolph and Sylvia Barlach as well, who were the other two contestants during the election, and I'm extremely grateful, and I think we should all be very grateful that they want to join our board and help our society in that way. So the results of the election could not have gone better for the entire society. Christa was program director at FOM, did many things there, including working on the report of the committee Dijkgraaf, FYSICA en Chemie 2025, and she became director at FOM. And after that, after reorganization, she became director of the Institute organization at NWO and is now scientific director at TNO Unit Industry. And I would like to give the digital floor to you, Christa.
Yeah, thanks a lot, Diederik, and also thanks a lot to everybody in the society that voted either for me or one of the other wonderful contestants. I'm very happy to join the NNV in this capacity. I've been a member for a long time, ever since I was, I think, a second-year student. But apart from that, it's great to be able to join and help physics in the Netherlands in this way. But my role today is to hand out a few prizes. And the first prize we're going to start with is the NTVN prize. And this is the prize for the best, let's say, public translation of your PhD work and explaining it well to the audience, the critical and the interested audience of the NTVN. Also this year, last year, we had these three prize winners. We have a wonderful jury with Claude Biemans, Arnoud van Enter, Vincent Ike, and Robert-Jan van Wijk. And they, again, this time had the wonderful task. I imagine that they had great fun in reading all the papers and then had great pain in trying to decide which one was actually the very best of them all. But again, they wrote, there were 6 people who were taking up the challenge and have written wonderful papers to be submitted to the NTVN. There's only 3 prizes, so unfortunately there had to be a choice made. But the criteria that the jury used were, first of all, do we understand what the PhD work was all about and what it added to the field? But also, was this paper written in such a way that we were fascinated by what these people did and where we helped by the way they use the language and the images in the paper. And the last one is possibly the hardest, because this might not be the thing that you train a lot during your PhD. So writing it in a relatively straightforward manner, but still make sure you give all the essential information, is really quite a feat. So letting go of the jargon and trying to be precise about what you actually mean is difficult, but these people managed very well. So without further ado, I think I can move on to announcing the prizes. And I think most of you already know, because it was, of course, in the April issue of the NTVN. But still, third prize was to, Robbie Albertsen for his paper on spin dynamics in atomic change. And he, to some extent, built the smallest physical or physics lab ever, where he was able to manage individual atoms and make a very, well, almost a lab test of spin waves. So congratulations to Robbie. I think I saw his name in the chat. Robbie, are you around? But if not, we move on to the second prize. The second prize is to Melissa Rinaldin. She was very clear already in the title of her paper what she wants to research. This is the geometry of phase separation and the influence of geometry in phase separation. And she makes clear why this is so important in nature. So because it's a rather complex subject, it needed a considerable introduction. But the jury felt that this was didactically very well done, and it didn't distract from getting the main message, because she came back to the subject and surprised the jury with the experimental approach. So congratulations to Melissa, well done. And the first prize winner is Julius Huids. He worked on time-resolved microscopy on the attosecond scale. And it's a well thought out story with helpful illustrations. It was easy to read the text, even sometimes almost a bit loose, but it was deceptive, the jury says. It was a deceptive looseness, because the author knows how to put enough details in the text that you, if you really want to understand what's going on, you will also manage to do this. So congratulations to all of you. Normally we would have gotten you on stage and applauded you, but you will be contacted about the prizes. And of course, we all were able to read your papers in the NTVN, in the last NTVN. And I think that is it for this prize. Congratulations. So
thank you.
We have one of the winners, Julius. Can you tell us a little bit about why you wrote the paper? We can take a few seconds.
Because when I was a student, I also read the NTVN, and I thought it would be interesting to once also write an article about it. So now that I had finished my PhD research and had a nice publication about it, scientific publication, I thought maybe this is the right moment to take up this challenge of writing an NTVN article.
Yeah. So thank you a lot, because I think a lot of people were well entertained by it, and it was also great that in this way lots of people managed to get the gist and essence of your PhD work. Thank you.
Yeah, well, it was nice to do.
Yes. So we move on now to the NNV Applied Universities Young Talent Award. So in Dutch we say HBO, but the translation is Applied University. And there's 3 applied universities of applied sciences that have an applied physics program. And this is Fontys, the Haagse Hogeschool, and Saxion. So listed, you see the 3 great winners of last year, Iris, Esther, and Sanne. But this year, there's another set of winners. Oh, so maybe before you move to the next slide, Diederik, what I'd like to say is that from each of these universities, we have one winner. So it's the best, it's a prize for the best performed internship during the 3rd year of their 4-year curriculum. And each university of applied sciences chooses one of the winners, and we can announce those winners. But also quite a few universities would like to acknowledge the full width of the talent they have in-house and of the difficulty, let's say, that they had in choosing the actual winner of their school in this competition. But in this case, they did manage, and we have 3 excellent winners. So the first one is, oh, we have a movie. Sorry, Diederik, I forgot about the movie. Can you start the movie?
Yes, the HBO's have an idea what it looks like from the inside. You're muted, Kirsta.
That was that was not clever. Anyway, I would like now to, because all these 3 great places apparently have lots of students who are enthusiastic, and I can imagine that if you look at it, you'd like to go back to school for a little bit and just be able to study physics once more, and maybe in an entirely different setting than when we all studied physics. So anyway, without further ado, I'd like to announce the winner. First, the winner for the Saxion University of Applied Sciences. That is Maaike van Dam. Maaike performed an internship at Demcon Krios on the development of a microcooler for electron microscope. She measured the vibrations of the cooler and found out where these vibrations came from. But the analysis of the measurements was of an outstanding level, and beyond the scope of her product, she realized also a standardized calibration setup for microcoolers. She worked independently in various structures, and this was made even more clear that due to the fact that we had the corona crisis, she had to work totally on her own in the lab. And I think this is really a feat for an intern to then be able to do your internship to such a high level. So she showed excellent experimental, programming, and professional skills. So for those of you who are looking for new employees, you have to wait another year because she still has a 4th year to finish at the Saxion Hogeschool, but it might be an interesting person to keep your eyes out for. So congratulations, Maaike. Maaike, are you in or not?
Yes, I'm in.
Yes, congratulations, Maaike.
Thank you. Thanks a lot.
Can you tell a little bit about your internship? Just a few seconds, but.
Well, yeah, it was at Demcon in Enschede.
Yeah.
And yeah, they want to use the cryocooler to use it in an electronic microscope, not electronic, a microscope, to make an 3D picture. And because of the cells, yeah, cannot move that much because of the image will be blurry. So that was my task, to find out how much it vibrated, the cryocooler.
Yeah, very nice. I
Yeah.
hope you also have fun this year in your final year at Saxion.
Thank you. Thanks a
Yeah.
lot.
Okay, so the next prize is the student from the Haagse Hogeschool. The winner at the Haagse Hogeschool is Luc Wiegbold. And he did his third year's internship at CERN in Geneva from September 2019 till February 2020. And he worked at the Isolde experiment, that is CERN's radioactive isotope lab facility. And there he did simulations on the reionization of sodium isotopes to be used in beta NMR experiments. He needed to find out the critical process parameters, but his results provided the design parameters that will be used by the R&D team to construct the new reionization chamber. And during this internship, he has shown that he can successfully perform an R&D cycle in a challenging, innovative environment such as CERN is. And I think he was lucky to be at CERN during the long shutdown, because from the picture I get, that he managed to get down into the tunnel. And that is, of course, always a highlight for any physicist. And I can tell you it's also a highlight for any person in the world. Anyway, Luc, congratulations on your prize. I don't know if you're in the conference.
I'm in the conference, yes.
Yes, hi Luc. We don't see you yet, but we have your picture up here. So can you tell us a little bit about life at CERN during lockdown?
Well, it was very, very calm. Everyone was working in the offices, and so it wasn't like a COVID lockdown, but it was the long shutdown.
Oh yes, of course, you were
so
before.
no experiments were being conducted at the moment. So everyone was working on theory and such. So but we can go like you could go down to CMS to have a look at it, because there was maintenance. People can show you the way, and so this picture is from CMS, if I'm correct, yeah. But also went down to Atlas to have a look at it. It was very cool. You can go to places where you normally couldn't go.
No, that's great. Thanks a lot, Luc. I get a note from Diederik that we're getting a bit late. So, but still, I'd like to announce the third winner from Fontys Hogeschool. That's Else Okkinga. Else worked at the Institute for Subatomic Physics at Utrecht University and contributed to an upgrade for the ALICE experiment at CERN. So she used data from the test beam facility, and she improved the calibration of a proposed detector prototype. So her supervisor was very pleased with the concise and well-written and well-structured report, and her work implies a significant step in the project that the group is performing. So contributing to the improved calibration of the future detector. She was very inventive and independent and had the proper critical attitude, reported even her results in international meetings, and answered many questions from a thorough background knowledge. So, and even that she managed to do in a concise manner. So congratulations, Else. I know, Diederik, that we're late, but we gave the floor to the other two. So Else, if you're in here, can you tell us a little bit about moving to how it was for you to be in at Utrecht University with the ALICE group?
Yes, hi. Thank you. And yeah, it was really great working with a lot of different nationalities, and I had some really great colleagues there. So it was really great.
Okay, thanks a lot, and to all three, and also the other nominees, many success in your studies. And now we quickly move on to the rest of the program. Thanks a lot.
Yes, congratulations, and thank you so much, Christa. We continue now to the FYSICA Prize. Each year, the FYSICA Prize is awarded to an eminent physicist who's working in the Netherlands. Fellow physicists can nominate someone, and a jury comprising of the chair of the Netherlands Physical Society, the chair of Stichting FYSICA, and a previous winner of the FYSICA Prize decide who wins out of all these nominations. And this year, the prize is awarded to Professor Daniel Bon, and he works at the University of Amsterdam and is an expert in his field of soft matter, a field that comprises of many different materials who can easily be reshaped like plastics or gels. He started a revolution in the scientific field that is about systems who are neither liquid nor solid, the complex fluids. And it's an interesting mix of very abstract meeting a bit of everyday. The materials are very well known to all of us, like blood, shampoo, and oil, for instance. And besides excellent work in many fields, from blood spatter analysis to environmental friendlier ways of spraying pesticides to ancient pyramids, non-physicists may have seen him last year in his efforts to see how his intimate knowledge centering around droplets and aerosols might help in understanding the spread of the coronavirus. I would like to congratulate him on the FYSICA prize, which is a very rightfully deserved prize. And I would like to thank him for giving a talk here about his work. And if people have questions, please put them in the chat and we'll try to ask them at the end. I would love to give the digital floor to you now, Daniel. And I know there are hundreds of people at this point applauding there in their own homes and enthusiastically awaiting your talk. So,
thank you, Diederik, and thank you also the Dutch Physics Society for the FYSICA Prize. I'm very honored. It's a great lineup of eminent physicists, and I feel very humbled being part of that select club of people. What I want to do, I will try and keep it short and snappy because we're already way behind the schedule. I will tell you how I got mixed up into the coronavirus and what physics can actually do to help us to combat the coronavirus. And so that is all experiments done in the last year. So it's not only the 100 years of the Dutch Physics Society these days, but it was also the anniversary of the pandemic last month. And so we will all agree that this changed our life dramatically, and so we need to really understand better the way that these viruses spread. And so if we contributed a little bit to that, I'm very happy. So aerosols and transmission of the coronavirus. I was just minding my own business, as Diederik already said. I'm very interested in spraying, for instance, in agricultural spraying, where drift of very small droplets pollute our surface waters. And so I was developing a number of tools to look at sprays and to look at the details of sprays to try and understand this a little bit better. When I got a question, an unusual question from the ICU ward of the Amsterdam Academic Medical Center. And so I don't know if you remember, but during the first peak of the pandemic, there was a shortage of respiratory equipment at the ICUs. And there was one special type of respiratory equipment that was not used because they were afraid that it would produce aerosols that could contain the virus potentially when they put the respiratory system on a COVID patient, and those aerosols could potentially infect the hospital staff. And so the question they asked around, and so also to me, is can we use this respiratory system, it's called a high flow nasal cannula, without any risk for the hospital staff? And so this is my colleague Antoine, who is trying out one of these masks. And you can also see our laser sheet that actually allows us to visualize these very, very, very small droplets. Yeah, we didn't realize, at least I didn't realize at that point, how much of these small droplets you actually produce. But those come from your saliva, and so if they contain, if you're infected with the virus, these small droplets may travel through the air and infect somebody else. Yeah, and so the virology of the virus is very complicated, but the virus transmission has to be done by these droplets, and so these droplets has to be transported, and so the conclusion is virus transmission is physics, and so we need to understand this a little better, and that's what we set out to do. And And so this is from a paper by our colleagues from MIT that shows you the anatomy, if you like, of a cough. And so this is the person coughing, and you see two types of droplets, basically. These green ones are trajectories of large droplets, and those are basically at the origin of the 1.5 meter rule. You can see that they fall onto the ground very rapidly. And so if you're not within the reach of those large droplets, you cannot get infected by these. Yeah, and so you should always keep 1.5 meter distance. However, there's also smaller droplets here shown in red. And you see that they have difficulties falling to the ground. And so if there's an airstream, they could actually be transported very, very, very far. And so if you want to understand how that works, you can go to YouTube and look at these dudes blowing smoke. And those are basically aerosol particles. They're the same size. And so you see that they really don't fall onto the ground. And they clearly travel more than 1.5 meters. And so if they contain virus, they're potentially dangerous. So from Antoine, who was trying the respiratory system, to what happens actually when you cough. So we use the same laser sheet you see here to visualize what happens when somebody coughs. And this is all that comes out, which is not very pleasant. But if you look very carefully, and I will play it again, you will see that besides the large droplets that, as advertised, fall onto the ground very rapidly, you can see all these little specks here, which are the aerosol droplets, and they seem to remain in the air for quite some time. Yeah, and so we first asked the question, like, what are these droplets? What happens when you cough? Yeah, and so what we did is we coughed into a laser diffraction system, and the laser diffraction is what we used for our agricultural spray to measure the drop size distribution. And that's where we first found something very interesting. If you cough, you produce really two types of droplets, as our MIT colleagues already suggested. Namely, they're small droplets between roughly 1 and 10 micrometers, and those lose a part of their water and become proper aerosols. The proper definition of aerosols is particles smaller than 5 microns. But you also produce these large droplets that are, again, at the origin of the 1.5 meter rules, and they're between 100 and 1,000 micrometers. 1 millimeter, and so there's nothing in between. So you produce two types of droplets. And another important finding is that if you simply speak, you actually only produce these aerosol droplets, and you get very much the same distribution of drop sizes as for coughing. Yeah, and so there's two processes apparently that lead to two types of droplets. You can ask the question then, how many of the droplets? And so we spent quite some time coughing into little sandwich bags, boterhamzakjes for the Dutch, because they're so light. And that allowed us to weight with a very precise balance the amount of fluid that comes out of your mouth when you cough or you speak. And so, just so you know, if you cough one time, you produce something like 700th of a gram. And if you say 10 times stay healthy, which is one of the key phrases that has been used in this type of research, you produce actually a lot less. Because of the large difference in size, the large droplets are 100 times larger, and so their volume is 10 to the 6 times larger. Most of the liquid is contained in the large droplets if you cough. However, there's still lots and lots and lots of these small aerosol droplets. If you do the calculation, you find, because we know what the size distribution is, about 20 million of these micro droplets produced in a single cough, and 7 million if you say stay healthy for 10 times. Okay, sorry. Now the danger of these aerosols, as we saw, was that they persist actually for a very, very long time. So this is an enhanced image of the laser sheet visualization that you saw. After 0 minutes, but just the large droplets have fallen, you see that it's really crowded with these thousands and thousands of small droplets. But after 4 minutes, there's still a lot. After 8 minutes, you can still see them. And even after a quarter of an hour, there's still a significant amount of these droplets in the air. And again, I repeat, if you if these droplets were produced by somebody who's infected with the coronavirus, and you walk into this room even 15 minutes after that person has coughed only a single time, you can actually still be infected by breathing these aerosol particles. Yeah, and so we found a way to actually artificially generate these aerosols, and I'm just showing this because it's pretty. So we have a very special spray nozzle from a company called MedSpray, and they can actually produce aerosol size droplets, and that allows us to actually fabricate a known quantity of these aerosols and look at how long they persist. And so that's what you see here. In red, you see a small room. Think of a public restroom, for instance, with the door and the window closed. And you see that the half-lifetime of the number of droplets is more than 5 minutes. If you open a small window, it already goes down to 1.5 minutes. And if you open the door and the small window, it actually goes down to something like 30 seconds. Yeah, and so this stresses the importance of ventilation for getting rid of these small droplets. And you might have seen me on TV over the last year saying the answer is ventilation, ventilation, ventilation. Now, the physics of this is, so I've simplified it a little bit here. I won't go into the details of the calculations, but these droplets are so small that the air drag on them is very, very large, which means two things. They don't get very far, so you need an airstream to actually transport them, but that is very easy because they're so light. But the air drag is also so small that they take a lot of time to sediment. And so it's the interplay between gravity, evaporation, and the initial velocity that gives this long persistence time. And so this is something that a high school physics student should be able to calculate, or maybe a first-year physics student at university. But we could compare it to our data, and we find that this indeed gives an excellent description of the persistence, not only for our data, but also for the famous group that started out with the stay healthy. Now you can, if you understand the persistence, you can also take into account the ventilation. So the ventilation is usually for a given room quantified as the number of air changes per hour, the number of times that the total air has changed over an hour. And 4 is something like a typical number. And so this is without ventilation, and you see that indeed the ventilation helps a lot because this is a logarithmic scale. Yeah, this is again the concentration of aerosols as a function of time. And moreover, we can, with our model, taking the ventilation into account, simply diluting the aerosols, account very well quantitatively for the data. Now, what you really want to do is, of course, is to know how much risk you run if you're in a room with an infected person. Now, the problem is that you, for that, need to do a little bit of virology, and we don't know much yet about the virology of the SARS-CoV-2 virus, but we actually know something about its small brother, the SARS-CoV-1 virus, which was a pandemic that many people have already forgotten, but that should have warned us. And it looks very much like SARS-CoV-2 and has an infection threshold that is estimated to be roughly 100 to 1,000 virus particles. Yeah, and so if you accept that SARS-CoV-2 is similar, then you can actually, from our persistence calculation and using the fact that you normally breathe something like 8 liters per minute of the air containing the aerosols as an adult human being, you can try and see what the risk is. The only other parameter, which is relatively easy to measure, is how much of the virus is there in your saliva, or the mucus of an infected person. And so those numbers are known. And so if you take the average viral load, you actually see that it's pretty difficult to infect somebody else. And so this is the time after the person has coughed that you enter in the room, and this is the time that you stay into the room. And so if it's green, it's completely safe. It's yellow, it's a bit unsafe, but not very. However, there are two types of person that you should try and learn how to recognize and avoid, which is the so-called super spreader. So we find from our visualization that there's people, when they cough, they expel 20 times more saliva than other persons. And so this could potentially be a super spreader. And even worse, there's changes in the amount of virus in your saliva while you are being infected. And so you shouldn't take the average viral load, but you should take the maximum viral load to exclude all risk. And so the maximum viral load is much higher than the average. And so if you're anywhere near a super spreader, you will get infected in this simple calculation. If you're near a normal person that is infected, you shouldn't stay around that person for too long, is the long and short of the explanation. Okay, that was perhaps useful, but not very useful, because some of you might be physics teachers and wonder why, whether your classroom is actually safe. And so the next question we ask is, can we actually do something about that? Now, this laser sheet is complicated because you need laser goggles and stuff like that. So we actually propose to use a clean room particle counter that actually does pretty well. So this is the drop size distribution in orange with the laser diffraction system that takes up half a room, and in blue with this simple handheld battery powered little device. And even the persistence, and that is of course what is important, is identical between this particle counter, and in green, if you look carefully, you see actually the results from the laser sheet imaging. Yeah, and so this is much simpler than the laser sheet, and you can leave the light on, which is also an advantage. And so just one example, if Diederik permits me, okay. Also one example, which is where this is an inpatient cardiology clinic with somebody on an exercise bike trying to do a cardiac stress test. Sorry. And so you can see that during the stress test, the number of particles in blue actually goes up quite dramatically. And so this can easily be measured with the handheld particle counter. What is interesting is that the CO2 actually gives a very good proxy for the number of aerosols. And in your classroom, you might consider using a CO2 meter simply, which are very cheap and easy, to actually see whether you should open the window and the door or not. The other thing you could try and do is use an air purifier. This is a plasma ventilation system. And so if I do exactly the same experiment, I see that the CO2 actually still goes up, but it completely destroys all the aerosols. It basically even filters out the dust that was present in the air. With that, the conclusions are there's a considerable risk of SARS-CoV-2 spreading by these aerosols, especially if you're near a super spreader, which might be somebody who expels a lot of fluid, but also has a high viral load. The solution is ventilation, ventilation, ventilation. And I learned a lot working with all the medical doctors and discussing with all the virologists. And this is something that might interest you about the impact of this type of research. It's truly interdisciplinary. This is what I got from the press service of the University of Amsterdam over 2 months. There were 477 million people who looked at, this was what they call the press coverage, who could have read about our research over a period of 2 months. And so over the past year, it's more than 600 million people, more than 500 million people could have read about our research. And if I say our research, I should of course acknowledge my collaborators from IOP, Stefan and Scott, MedSpray and IOP, Kees van Rijn, AMC, Reinoud Bem, the Cardiology Center, Arnoud Somse, and the VUMC, Leo Hofstra. And if you want to read more, you don't need to write this down because everything is being filmed, right, Diederik?
Yes, yes, it is.
So on that, I thank the Dutch Physical Society again for awarding me this prize, and I hope I've shown you a little bit about what research can do for research in physics can do for understanding virus spreading. Thank you.
Thank you so much, Daniel, for your presentation. And again, congratulations with your prize. And thank you for trying to help advance the discussion about Corona and the endless debate between aerosols or not. Due to the time constraint and the fact that Detlef Loze already answered a few questions on the chat on your behalf, and I think he's eminently qualified to do so.
Thank you, Detlef.
So if you do not mind, the next speaker has some other obligations. So I thank you so much, Daniel, and most of the questions that were asked that were not answered by Detlef were also answered by yourself in the latter part of your presentation. So thanks again, congratulations again, and I would like to give the floor to the next speaker, and before I do so, every speaker will receive this wonderful engraved glass to honor our centennial. It's a small token of our almost sheer infinite gratitude. We continue to Jeroen van Dongen. We are honored to have a professor of the history of science in our midst, and he works at the University of Amsterdam and is co-director of the Vossius Center for History of Humanities and Sciences at the University of Amsterdam, and also a counselor of scientific integrity since 2018. I would like to invite him to take the digital stage over from me and give a talk on the history of Dutch physics and the founding of the Netherlands Physical Society. So if you are there, I'm sure that everybody is standing on the benches to applaud you from home, and I wish you the floor.
Thank you, Diederik, and thank you also. Well, first let me offer my congratulations to the Dutch Physical Society with its centennial celebration, and also my congratulations to Daniel, my esteemed colleague from Amsterdam, with winning this year's FYSICA prize, and of course also all the other prize winners. I'll offer a brief, let's say, entertainment about the history of the Dutch Physical Society and Dutch physics over the past century. As Diederik has already told us, the Dutch Physical Society was created in April of 1921 at a meeting in Utrecht. The specific purpose of the creation of the Dutch Physical Society was to have national meetings, national lectures for physics research. Meetings were alternating between Utrecht and Amsterdam. The journal, the Dutch journal FYSICA, also as subtitle Nederlands Tijdschrift voor Natuurkunde, was already in existence. These meetings were reported then in that journal. Membership rose fairly rapidly, doubled in about a year, but still very low numbers, growing to about 700 people registered members at the end of World War II, 1945. Now, the creation of a Dutch physical society, or of a physical society, is quite a moment in a scholarly discipline. One can even argue that the discipline of physics more or less comes into existence with the creation of the Physical Society of Berlin. So physics was a subject that did not really exist as such prior to the 19th century, and at particularly the University of Berlin, research was taken on as a responsibility for university professors in the philosophy department predominantly. Within the philosophy department, there was some tension between those that were interested in more doing more speculative thinking, people like Hegel, and on the other hand, people that emphasized more factual knowledge. Now, these would develop into, on the one hand, let's say, historians that emphasized, facts about, human history, and on the other hand, let's say physicists, those that emphasized facts about nature. And they organized themselves in a physical society, the Berlin Physical Society, 1840s. Eventually, that turned into the German Physical Society, and that was then the model for the Dutch Physical Society that came into existence in the 1920s. Now, the German society kind of defined the field, what it meant to be a physicist, and then you can say that the Dutch Physical Society, the creation of the Dutch Physical Society, sort of signals the maturity of the subject in the Dutch context. Now, what was Dutch physics like? And as we already could see in Diederik's presentation, Dutch physics was, at a very high level of quality. Now, this is one of the buildings of Dutch physics of those days. This is the physics department of the University of Amsterdam, where some of these meetings were being held. And the following document may illustrate a little bit, again, the quality of Dutch physics. So this is Paul Ehrenfest at Leiden, who's writing his close friend Albert Einstein, offering him basically a professorship in Leiden. So if you could please read with me. Dear Einstein, we must attach you to Leiden. It's simple, provided you just say yes. We will arrange everything in no time according to your wishes. You'll get as much remuneration as is necessary for you, your children, whatever else. Absolutely no lecturing duties will be imposed on you. You can take as much time as you'd like to work in Switzerland, elsewhere, as long as one can say Einstein is at Leiden there's Einstein. So clearly, for Ehrenfest to just be able to make this offer and believe that, it will stand, that this can just happen, to include the world's leading physicist at that point in Leiden without any sort of second thought, illustrates the opportunity that existed. It may further be illustrated if we continue reading. It may interest you to hear that Honest especially, not to mention the rest of us, is very enthusiastic about the idea. Here you will have in your immediate proximity Lawrence, de Sitter, me, Kunen, Droste, de Haas, his wife, Fokker, Burgers, Julius Zeeman, and will regularly see intelligent and impressive young fellows of pleasant personalities. Moreover, guests like Nordstrom, Borg, etc. So one other way to understand the role of Dutch physics is to look at the picture you see there. You see Ehrenfest next to Einstein, Paul Langevin, Kamerlingh Onnes, Pierre Weiss. These were a German physicist, Albert Einstein, meeting in the Netherlands, this is in the living room of Kamerlingh Onnes, French physicists, discussing the theory of superconductivity. So not only does it illustrate the quality of Dutch physics, it also illustrates the role that the Dutch saw for themselves, connecting the major cultures of physics in a divided Europe, right? This is shortly after the conclusion of World War I, when many scholars across the warring countries of World War I were not willing to talk to each other, but the Dutch saw a role for themselves to reconnect basically the international world of scholarship, and that's how they defined themselves during that decade. The quality of Dutch physics may be further illustrated by this document. Now, this is an article written by Johannes Droste. The name was mentioned earlier, and Droste was a graduate student of Hendrik Antoon Lorentz. The title of the article is "The Field of a Single Center in Einstein's Theory of Gravitation and the Motion of a Particle in that Field," from the Proceedings of the Amsterdam Academy. Now, if you continue reading the article and note the date, May 27, 1916, what you see here in formula number 7 is in fact the equation for the line element of a point particle. In other words, this is the equation for a black hole. And we'll see a number of esteemed speakers later today that will tell us much more about black holes. But basically, this is you know, one of the earliest publications of the central equations of a black hole. Now, Droste did not understand it as a black hole. He had a, if you read on there in the second sentence, you can see that he had a sort of well, a left-handed understanding of general covariance in the general theory of relativity. And in the footnote, he mentions Karl Schwarzschild, who had published the same equation a little bit before. So now we know this equation as the Schwarzschild equation. But it illustrates, you know, once again, the quality of Dutch physics. It also illustrates the central role that the Dutch played in studying and sharing the knowledge of the theory of relativity. If you wanted to study relativity theory at this point in time, Leiden was the place to be. And indeed, again, due to World War I, no communication across the English Channel, for instance, except through the Dutch. So it was the Dutch, de Sitter in particular, who brought knowledge of.
Oh, Jeroen, your camera's on me.
Yeah, I think I was accidentally muted. Anyway, so it was the Dutch who basically spread the knowledge of relativity theory, you know, beyond the European continent, particularly to the United Kingdom. My talk is suffering now from a halted PowerPoint, but here I'm back again. Okay, so 100 years of Dutch, the Dutch Physical Society is of course 100 years of Dutch physics, and 79 of those 100 years are years in the 20th century. And arguably the 20th century is the century of physics. And we see that illustrated, of course, also in the history of Dutch physics. Now, the period I was just talking about is known in the historical literature as the Second Golden Age, referring, of course, to the 17th century as the Golden Age. The Second Golden Age is a term not just reserved for physics or for science. It's held to apply to you know, broader Dutch culture, but of course particularly true for Dutch physics, which does stagnate and decline a bit at the end of it, with the passing, let's say, illustrated by the passing of Lorentz and Ehrenfest. Stagnating a bit, falling further behind, declining yet more during World War II. Yet after World War II, a major new opportunity, major new investment is taking place. And that is, in fact, largely to be attributed to the detonation of the atomic bomb in Japan. So during World War II, scientists tried to keep working as much as possible as they could. Those that ended up in positions of power shortly after the Second World War did not particularly appreciate this attitude. It was strongly felt that the Netherlands needed a, let's say, moral regeneration, and one was not looking at technology and science in particular to facilitate this. One was looking in quite different directions. Yet the detonation of the atomic bomb completely changed the dynamics. You see that again illustrated in this quote here. And this is of H.B. Dorgelo, was president of the Physical Society in 1945, later became the first rector of the University of Eindhoven. So in this quote here, he first emphasizes teamwork as, you know, a new way to organize science. He secondly also emphasizes, and let me read that in second paragraph now in Dutch. Mogen de wijze van samenwerken van groot belang zijn, nog belangrijker is het doel waarvoor men dat doet. En dan gaan, terwijl ik deze woorden uitspreek, september 45 of course, onze gedachten als vanzelf uit naar de atoombom. Het nieuwste product van samenwerking van een staf van fysici en technici en de duizenden die onbewust aan hun doelstelling hebben meegewerkt. Een mengeling van gedachten bestormt ons als wij daaraan denken. So of course, the atomic bomb really changing the dynamics of science in the Netherlands, but of course not just in the Netherlands. So what we're looking at here is a diagram that counts the number of PhDs awarded in the United States throughout the 20th century. And of course, initially it's a bit of a trickle, growing steadily, declining during the war years 40-45 due to the fact that many students are serving in the military. But then a very, very quick acceleration sets in, leveling off 1950s. And then after 58, actually a further expansion, and that's then due to the launch of Sputnik, which informs the Americans that they need to expand their efforts in fundamental science yet again. And so these are American numbers, but they're easily transferred to the Dutch situation. And in the case of the Netherlands, we then, of course, immediately think about the creation of FOM. So I mentioned earlier that political leaders were not particularly interested in investing in fundamental science. Yet that completely changed after the detonation of the atomic bomb. Leading Dutch physicist Kramers, Koster, wrote to the Prime Minister alerting them to a need to invest here. And in political circles, this was recognized. The idea was then to invest heavily in fundamental science, in nuclear physics in particular, not to develop anything like technology that could lead to a weapon. The idea was that this was beyond the reach of the Netherlands, but one needed to invest in reactor physics. Why reactor physics? Well, for the opportunity that this offered, but particularly it was understood that having fundamental knowledge of first rate yourself meant that you could be included in collaborations in the Western alliance as it was taking shape. If one did not have one's own knowledge to contribute, it was seen that one was going to be of a second-rate type of a player and would not be included in further knowledge sharing. So it wasn't even so much that you could have your own knowledge to do things. No, you needed knowledge in order to be a partner to sharing of knowledge. This applied in the case of fundamental physics, therefore the creation of FOM, initially very much limited to nuclear physics, but gradually expanding. It was matched with investment in military relevant science, and there again an emphasis not so much on science that you could apply on, let's say, the battlefield tomorrow, but to the frustration of the military itself, Dutch military. Again, an emphasis on fundamental science. And why fundamental science? It was understood that fundamental science was one of the Dutch's strengths, and therefore, investing in something you're strong in will help you being a valued partner further down the line. Now, in the discourse on this kind of investment, the emphasis was very much on collaboration, on team building, on team effort, on planning instead of competition. The partners that one imagined were ideally the Americans, but the Americans initially in the first years were not interested in sharing knowledge at all. They already had a partnership, particularly with the UK, which was the other partner that the Dutch very much wanted to be included with. The English then were looking to the US. The US basically blocked the English from sharing their knowledge beyond their own partnership. So it ended up that the Dutch started collaborating with the Norwegians and to a lesser extent with the Belgians. And these collaborations were very successful. So then when the early 50s came around, the Dutch, together with the Norwegians, did have a working reactor and other kinds of knowledge, which then led the Americans to open up. The Dutch were part of the American. One of the reasons why the Americans decided to open up more. The Dutch were then very much included in the, let's say, Western Alliance effort to build a strong infrastructure in science that was shared across the West. Okay, and well, that's my brief, let's say, entertainment about 100 years of Dutch physics and Dutch physical society. Now, as an historian, you're sometimes asked what the next 100 years will bring. And unfortunately, unlike physics, history is not a predictive science. But I do believe that one can learn from history. And I hope I will have contributed some learning today. Thank you very much for your attention.
Thank you so much, Jeroen, for this interesting talk. Christiane mentioned something that I found very staggering as well, that the letter you read out loud mentions De Haas, comma, his wife, instead of the name. Is there a specific reason, or is that just a chauvinistic century-year-old kind of way of doing it?
I think a bit of both. Yeah, it's true that she doesn't, or Ilfes doesn't mention the wife's name. So the thing is, De Haas and his wife were close friends of Einstein. So in that sense, there's a bit of personal relationship there that you know, Einstein would immediately know who they are talking about. But she was very much a physicist in her own right, and yes, it's an illustration of the fact that you know, unfortunately in those days women were often seen as an appendix to their husbands. Yes.
Thank you so much, Steven, for this talk. If you could stop your screen sharing for just a moment, we will send you, of course, a glass engraved, and thank you so much for giving us a little bit of taste where we come from. And that always helps to know where we're going. It's time for a small break. I hope that everybody, it's going. Sorry, it's time for a small break, and we will be back here in about 5 minutes, and we'll continue with these great speakers. One thing I would suggest, we still have a long program to go, so take these 5 minutes just to get up, make some coffee, and just move, because it really always helps. And I always think too late, oh, I wish I should have taken my break. So we'll be back here in about 5 minutes and continue with our program. Thank you. So, hello everybody. I hope you are all still here. Wondering how, what beautiful things the next steps of our program will be. And we will start now with our Young Speakers Contest. And Young Speakers Contest, every year on the FYSICA meeting, a prize will be awarded for the best oral presentation by a young scientist. And the contest aims at younger colleagues, especially those in their final years of the PhD program or postdoctoral research with not more than 5 years of professional experience after their PhD. The presentation has to focus on the own scientific work of the candidate, and a panel has narrowed down a long list of candidates down to the 3 best. And today we're going to be the judge of who will be the winner, and this will be up to you, the viewers of this FYSICA conference. You will have to judge who will give the best speech, and they will win the Young Speakers Award and get a cash prize of 750 euros. And every year, I think this is really a treat because they get exactly 10 minutes, nothing more, nothing less, to get to learn. So we get to learn about 3 completely different topics, and they are all very well versed in bringing this across in a perfect manner. And at the end of the 3rd presentation, you will get the chance to vote who you thought was best. And you will get sort of a voting module inside Zoom, and you have a few minutes to cast your vote. And then we will know who will win the Young Speaker Contest Award. The first to start giving a presentation is Sonakshi Arora from the University of Delft. And I would like to give her the floor.
Yeah, it works.
Wonderful.
Perfect. Okay. Good afternoon, everyone. It's great to be here. My name is Sonakshi, and I'm a PhD candidate in Delft University of Technology. I'm currently working in the nano-optics group led by Kobus Kuipers. And the story that I want to tell you today is actually a result of a close collaboration with the group of Ewald Verhaken from AMOF. So that I actually have a lot of people to acknowledge, but especially a big thank you to Thomas Bauer and René Barczyk. Okay, so if I ask you to name one thing that you could not live without, what would it be? Maybe that list is a bit too long for today's talk, but one thing is for certain, that you and I wouldn't be here in these current times if it wasn't for the internet. The internet connects the world in ways that has made life comfortable as we know it. The internet, as some of you may know, is connected of lengths of fiber optics. And these are networks that actually carry light in small packets called photons over extremely large distances. This means that the signal travels at the speed of light, negligible losses, and an extremely high bandwidth. That's quite interesting because this signal has to travel thousands of kilometers to connect us to, say, someone sitting in Australia without dying out. For this reason, we have what we call data centers, for example, Facebook, Amazon, or even Google, that are large-scale, high-end facilities that act like traffic cops and process this data. So it's here, in these data centers, that this light gets converted into electronic signal using circuits. But the signal now, because it's electrons, they're much slower and it's less efficient. And that unfortunately also means that it generates a lot of heat and it consumes a lot of power. So about 20% of the world's energy is expected to be consumed by these data centers. Okay, so why don't we just let light keep doing its magic and use optical chips instead of electrical ones? And then data can travel without any losses. Fine, perfect. We have optical chips. It transfers data at the speed of light. It's extremely efficient and there are no losses. Not so easy, because optical chips, as useful as they might be, they do suffer from scattering losses, which means that if there's a defect or a corner along the path of the signal, it can lead to scattering and the light gets reflected back, which means it doesn't reach the output. That's a big problem, but maybe one that can be solved. In 2016, there were 3 condensed matter physicists who won the Nobel Prize for their theoretical work on topological materials. Let's see what topological means. Topology is an abstract concept. It says that a material retains its properties or its behaviors, even if you change its size or shape. But what does that actually mean? So for a topologist, a coffee cup is the same as a donut, but it's not the same thing as a pretzel. Why is that? Because for a topologist, a coffee cup and a donut can be defined by a topological quantity, which is given by the number of holes it has. So a donut has 1 hole, whereas a pretzel has 3. And theoreticians say that when you bring these 2 topologically different objects together, something magical has to happen at the interface. So if I throw some electrons along this interface, no matter what defect it encounters, it will always travel along the same direction in one direction, and it never gets scattered back. Perfect. That's exactly what I'm looking for light. And I also wanted to work for my experiments. So we borrowed these concepts from these topological concepts from solid state physics, which is the study of electrons, and used it in the study of photons or photonics. But okay, this photonic world has this donut pretzel situation a bit different. Like electrons travel in an electronic lattice, light travels in a photonic lattice, which is given by these periodic structures. And in conventional crystals, we see that light gets scattered back when it encounters a defect or a sharp corner. That's quite a shame, because we lose most of this light at these corners. It reduces the total efficiency of the crystal and makes it quite unusable for communication networks. Okay, but if we take this crystal and we add a bit of topological spice to it, things surprisingly change. In a topological crystal, the symmetry of the periodic lattice is arranged in a special way so that the interface allows the light to pass through without any losses. Okay, so we take a look at the real image of the crystal and see what this interface actually looks like. So on the right side, I have an SEM image of the crystal that we work with. Let's play a short game. I'll give you a few seconds, and it would be nice if you could find out where the interface is on this right image. I'm sure most of you did manage, but maybe this helps as well. So what we have here are 2 topologically distinct lattices with different topological quantities that form an interface. And it is here that light suffers no back reflections, even if there are sharp corners, making this entire transport unidirectional and robust. But when we say robust, how robust is robust? In order to answer this question, we use a near-field optical microscope. It's an experimental setup. And from this, we get the full detailed information about the light that's traveling along this crystal. Let's see what that looks like in actual experiments. So here we have the image of the electric field amplitude of light that's traveling in these experiments that has not just one, but 4 sharp corners. That's pretty cool, because what we see here is that light is confined to our photonic crystal structures, which is as small as the nanometer scale. That's about 100 times smaller than the diameter of a human hair. Okay, so we have amplitude and we have phase information. What that means is we know exactly how much light is moving in the forward direction and how much is moving in the backward. And now if we do some simple math and we take the ratio of these quantities, we get what we call the degree of robustness. This number tells us exactly how much light is allowed to pass through the entire length of the crystal. So higher this number, lesser the amount of back reflections at the corners, and more protected this crystal is against losses. Now, if we use that information and we compare a topological to a conventional crystal, turns out that a topological crystal is not just better, but it's 2 orders of magnitude more robust than a conventional one that does not have these topological properties. What that means for you and me is that we can actually use this technology to design optical chips that can now hold 100 times more corners or even much more complicated networks without the fear of losses. With this, I would like to thank you very much for being here and for your attention.
Thank you so much, Sonakshi. Very well done. I think we all agree, and the people are applauding at home. And it is time to go to the next speaker of the Young Speakers Contest, and that is Thijs van Eden. So I'm going to give you the floor, Thijs.
So good afternoon, everybody. Let me wait for my slides.
Participant में दबाओ, उसमें raise your hand.
Okay. So, good afternoon, everybody. My name is Thijs van Ede, and I'm a particle physicist working at the NNV Institute in Amsterdam. So today I want to explain to you how we learn more about the most distant and mysterious objects in our universe by looking at particles at the bottom of the Mediterranean Sea. To understand how we end up at the bottom of the sea, we need to go back in time. So for as long as we humans walk this planet, we look up to the sky, we see the stars, and we catch a glimpse of our universe. Nowadays, we know there's a lot more to the universe than the eye can see. We are continuously bombarded with energetic particles and radiation coming from outer space. The puzzling thing, these particles can be 1,000,000 times more energetic than the particles in our most powerful particle accelerator here on Earth, the LHC at CERN in Geneva. What kind of objects can create these extremely energetic particles? My work is focused on finding their origin. So why haven't we found their origin yet? Let's take a look at a mysterious object somewhere far away. Traditional astronomers would look at the light this object is emitting. But if this object is very far away, we run into problems, because if light hits matter on the way, it interacts, and then we don't see it here on Earth. The majority of particles that arrive here on our planet are charged, but charged particles follow a curved trajectory due to the magnetic fields present in our universe. And when we detect them here on Earth, it's difficult to point back to where they came from. So today I want to present you the solution, and that is the detection of neutrinos. Neutrinos are chargeless particles, and therefore they travel through a universe in a straight line. They are famous for their tiny, tiny interaction probability, so they can travel through dense areas of space without interacting. And this makes them the perfect messenger from these mysterious and distant objects. The majority of neutrinos pass right through our planet. They pass through you, they pass through me, but 1 in a billion interacts. So let's take a look at a neutrino entering one of our oceans. If this neutrino interacts, it will produce a charged particle. These charged particles do something very interesting because they go so fast that they exceed the speed of light in water. This produces a shock wave of light that we can actually see. We can compare this optical effect with a similar acoustic effect that everybody knows. If a plane travels through our sky and it exceeds the speed of sound, the sound waves bunch up behind the plane, forming a shock wave. And when this plane passes you, you don't hear anything. And then suddenly the shock waves catches up with you and hits your eardrum with a very loud bang. We have something similar happening underwater, but then with light instead of sound. So we have these neutrinos flying through our universe. They pass our planet, and every once in a while, they show us a faint light. What can we do with this? If we want to detect this light, we need to build an extremely large detector because these interactions of neutrinos are extremely rare. The perfect place for something like this? The bottom of the Mediterranean Sea. Researchers and scientists from all these countries are working together to build a neutrino telescope. The name of the telescope is KM3net, and it's being constructed at the bottom of the Mediterranean Sea near Sicily, where this black star is. If we go below the surface near Sicily, we find our detector at 3.5 kilometers in depth. The detector consists of a cubic kilometer of seawater that's instrumented with very sensitive light sensors. These light sensors are placed within glass spheres. And if we take a look at one of these glass spheres, you see 31 eyes, and these eyes are the sensitive light sensors that can detect single photons. We place these glass spheres in a three-dimensional grid at the bottom of the sea. And if you take a look at a sketch of how our final detector would look like, you see over 2,000 of these glass spheres here. And now, if a neutrino interacts in the vicinity of our detector and a charged particle enters it, you can see a trail of light that will be detected by our sensors. Our sensors detect light at the bottom of the sea, and they send the data to shore. The data consists of two things: the time at which light was detected and the position of the sensor that actually saw the light. So when this data reaches shore, it is sent to my home office. This is where I work, probably like the rest of you as well, working from home. And here I work on algorithms that translate this data, translate these light patterns to the direction of the particle that produced it. It's important that this is done very efficiently because we get tons and tons of data from the sea. And secondly, we need to make this translation as good as possible because the better we determine the direction of the particle, the better we can determine its origin. So how do I do this? Let's take a look at an example. We have our detector, a charged particle produces light, and our sensors, they see it. In real life, we don't see the direction of the particle, we only see the light that is detected. How do we make this translation from light patterns to the direction? The key to this is doing extensive simulations. In my work, I simulate particles and light underwater, and I try to get an idea of how much light a sensor of us would see if a particle passes by. In these simulations, we find out that the amount of light depends, for example, on the distance of our sensor to the trajectory of the particle, the energy of the particle, the water properties. And these simulations together provide us a probability that our sensor would see light depending on what happens in our detector. These probabilities are the key to translating the data that we get from the sea to the direction of the particle. So let's go back to our detector. We have this light pattern and we want to figure out the direction of the particle that caused it. What I do, I hypothesize a direction of a particle and figuring out, is this the direction that produced this light pattern? What I do then is I calculate for all the sensors the probability that this sensor would see light if a particle passed in this direction. When I have these probabilities, I can multiply them to get a likelihood that this light pattern was produced by a particle going in this direction. I repeat this process for a different direction. I obtain new probabilities, a new likelihood, and I could do this for a whole bunch of directions, and I compare these likelihoods, and I pick the direction that has the highest likelihood, telling me that this light pattern was produced by a particle going in that direction. So the algorithms that I write, they typically give an estimation of the direction of the particle. So let's pretend that this is my estimation of the direction of the particle, where the triangle represents the error. If we map this direction onto a sky map, you see that it's a huge part of the sky from where this particle could have come from. There could be millions of objects there that could have produced this particle. It's therefore very important to make this translation as precise as possible. In our detector, we can actually pinpoint the direction of particles like this. And the key to that are those simulations that I talked about. The better we understand particles in our detector, light, and everything that happens underwater there, the better we can make this translation from light to a direction. And then we can pinpoint an origin of a particle on the sky map like this. And when we can do it like this, we are in an excellent position to work together with scientists and astronomers around the world to figure out what kind of objects are there that are creating these particles. And hopefully, this will help us to solve the mystery surrounding these extremely energetic particles flying around in our universe. So today, I gave you an overview of my work and what we're trying to learn about the universe at the bottom of the Mediterranean Sea. I hope that when this curfew is over, you're allowed to go out again at night. You take a night stroll, you look up to the sky, and you remember, there's more to the universe than the eye can see. Thank you.
Thank you so much, Thijs. Thank you for your wonderful presentation. And luckily, even within the curfew, when you're at home, neutrinos will always bombard you wherever you are. Thank you so much. We will go to the next speaker, and that is Adela Melkrova. I hope I pronounced your name correctly. And I would love to give you the floor if you are there, Adela.
Yes, I am here.
Excellent.
So, good afternoon. After hearing about particles coming from large distances in the universe, I would like to scale down quite a lot to nanometers scale and take you on a short trip to the world of biophysics, where we use the methods of physics to study living matter. On the background image is resistant bacteria Staphylococcus aureus, which is causing problems worldwide, infecting people with open wounds after surgeries or accidents, and not really responding to current antibiotics treatment. After 60 years of antibiotics usage, nowadays 1/3 in the European Union and more than a half of these infections in United States are caused with resistant strains of bacteria. So we need to search for novel approaches how to treat these infections. And my approach is to use the physics on a molecular level to better understand the interaction between antibiotics and bacteria. Today, I will present you with a very promising candidate which combines quite uniquely some unexpected molecular mechanisms. The candidate is called AMC109. It was designed in a Norwegian pharmaceutical company, Amicode, according to a minimal pharmacological model for a surface active molecule. Such a molecule has to have a hydrophobic part and a hydrophilic positively charged part. This molecule was successfully tested against broad range of bacteria in clinical trials, including the resilient strains. So far so good, it works, but nobody actually knows how it works. What is the physics behind its activity? And this is my scientific question. I am particularly interested in bacteria Staphylococcus aureus, but I will call it bacteria for the simplicity. The surface of bacteria is covered with the cell wall. And one of the main parts of the cell wall is the membrane. Membrane is depicted here on the schematics. It looks like a bilayer of phospholipids, and it also contains lipid domains. Lipid domains, here depicted in yellow, are parts of the membrane which are slightly thicker than the rest of the membrane. They are usually more rigid, and they fulfill some important functions in living cells. For example, without the domains, the cell wouldn't be able to synthesize the material for the whole cell wall. And the cell wall is needed to maintain the mechanical stability of the cell. And the membrane is also the main target of these antibiotics. So my scientific question is quite concrete now. How does the new antibiotic, AMC 109, affect the membrane of bacteria, as this is the main target of it? And to answer this question, I combine a variety of biophysical approaches. First, I have a look at the membranes of bacteria with classical atomic force microscopy. The changes, the dynamics of the changes induced in the membranes with these antibiotics are viewed through high-speed atomic force microscopy videos. And the molecular level view on the interaction between the bacteria and the membrane are viewed in computer through molecular dynamic simulations. Now, the main power of the experimental methods is their remarkable resolution. Atomic force microscopy is a purely mechanical approach where we have a small tip which scans the surface of our sample and reconstructs the height profile of the sample. With this method, we can go to nanometer or even sub-nanometer resolution, so we are really observing individual molecules or clusters of molecules. Having said that, let's dive into the results. Our first question was quite simple. What happens with the molecule when we put it to the water solution? Quite simple question for the start. If we remember the physical chemistry of the molecule with the hydrophobic part and the positively charged hydrophilic part, it's not surprising that the hydrophobic interaction immediately drives formation of stable aggregates in water, hiding the hydrophobic parts inside, and only the positively charged parts, here depicted in blue, are sticking to the water phase. We identified this aggregate to be the functional particle actually attacking the membrane, depicted here. And now I will show you a short video from the molecular dynamics simulation, which is just simple solution of Newton's equations of motion for the system of molecules. And you can see here how this aggregate comes from the water phase, attaches to the membrane, and gradually dissolves all the antibiotic material in between the molecules inside of the membrane. We noticed here that the main driving force for start of this interaction is the electrostatics. The aggregate is positively charged at the outside, and the membrane has to be negatively charged to start this interaction. So the electrostatic interaction drives selectivity for only negatively charged membranes. And the negative charge is the main difference between the bacteria cell and human cells. Bacteria are negatively charged and human cells are neutral. So the electrostatic interaction drives selectivity for bacteria over human cells. So now let's have a look what it actually does to the bacterial membranes. And for that, I employ the atomic force microscopy. Here is the series of images from atomic force microscope on the bacterial membranes. The yellow parts here are the membranes laying flat on a hard surface. When I add the antibiotic molecules, then in some certain concentrations, the membrane loses its mechanical stability and structure and spreads. If I add even more, it spreads more and covers the whole available surface area. Importantly, we observe no perforation, no holes in the membranes. This was quite surprising because the majority of membrane active antibiotics actually perforate the membranes. Here for comparison is this very same experiment with pore-forming antimicrobial peptide. And you can see how the membrane looks like. It's full of holes, there is debris laying around, quite different from the activity of AMC 109. So we can clearly conclude that AMC 109 acts differently than pore-forming agents. And now this was intriguing for us, because if it does not perforate the bacterial cell, does not make holes in it, then what does it do to bacteria that this kills it? And we believe that we found the answer to this question again in atomic force microscopy images. Here is the image of bacteria membrane without any antibiotics added. And you can see these little bumps there. These bumps are the lateral membrane domains. I was talking about that previously, that these domains are needed to synthesize the material of the cell wall to maintain the mechanical stability of the whole cell. And what we noticed, that if we add the antibiotics, these domains, the lighter parts, are scarce. And if we add even more, they are completely gone. We had a closer look at this phenomenon via high-speed atomic force microscopy video. Here on the video, you can see the lighter patches, which are the lateral domains, moving rapidly all around the membrane. And then we add the antibiotics now, and after a few seconds, these domains slow down their diffusion, they cluster together in the center and at the edges, and then they dissolve to the surrounding membrane, and they are completely gone. But without these domains, the membrane cannot fulfill its function. It cannot synthesize the cell wall. So the cell loses the mechanical stability and gradually dies. So to sum everything up, I hope I convinced you that this molecule here combines quite unique molecular mechanisms. First, the hydrophobic interaction leads to aggregation, which by itself is quite unique among drugs, because when we design drugs, we usually try to avoid any sort of aggregation. But here, the aggregation leads to exposure of the positive charge, and then the electrostatic interaction drives the selectivity for bacteria. When the antibiotics is inside of the membrane, it changes the lateral organization and the packing of the molecules inside, which resembles the activity of small disinfectant molecules. And disinfectants are quite powerful, but their main disadvantage is that they kill everything. They are highly toxic also to human cells. But with this molecule in hand, we have a disinfectant which is highly selective only for bacteria. And with that, I would like to thank all the people involved in the project and thank you for your attention.
Thank you so much, Adela. Thank you so much for your presentation. Thanks to all three. I would like to, I thank all three, of course, for your presentations. You saw Sonakshi with the robust topological solutions to light scattering in, for instance, internet communication. We saw Thijs with probabilistic. Gaat daar iets? Deze zocht ik. Oh, sorry. With probabilistic algorithms, I'm sorry, to understand where Mediterranean neutrinos come from, and Adela with the quest to understand how antibiotics physically interact with bacteria membranes. It is now, sorry, there's some digital things going on here. Okay, it's now time for you to vote, to cast your votes for which one you think gave the best presentation. And right now, a voting pop-up pops up where you see the three names, and all you have to do is click one of them and press the submit button. It is important that you do so. It will be open for a few minutes and then it closes, and later at the later in the conference we will hear who won the Young Speakers contest. And before we go on, I would like to briefly mention that these 6 sponsors have our sincerest thanks, because without them, this would be much more difficult. They are making this possible. So thanks to Philips, Hamamatsu, Quantum Design, ASML, Lawrence Center, and Molenaar Optics for making this conference possible. So please don't forget to cast your votes for the Young Speakers Contest. It will only be possible for a few minutes. And now I think it is time to move on to the next 2 speakers. I don't know if you've heard of this, but there is a wonderful art meets science meets, I don't know, Banksy sort of project going on, where the most beautiful formulas and physics discoveries are put on walls. And to say a little bit about this, I would like to give the floor to Ivo van Vulpen and Sens-Jan van der Molen. And I believe, as if I understand correctly, that Ivo will start. And in the meantime, don't forget to cast your vote if you haven't already done so. Ivo?
Yeah, thanks, Diederik. Thanks for the invitation. Well, we're here today at FYSICA to share our passion for physics, our shared passion for physics, and to talk about ongoing research. But I mean, outside our audience, there's of course an even larger audience outside this meeting that is also interested in what we do, or could be interested in what we do. Now, sharing knowledge about physics and our passion for physics is of course not always easy. I mean, people like Diederik or Julia Kramer or Anna Gimbrere or Raza Muller, they do that on television for a wide audience, but there are many more initiatives. And I want to talk to you about one initiative. So together with Sens-Jan van der Molen, who's a colleague from Leiden, a physicist, and 2 artists, Ben Walekamp and Jan Willem Bruins from Leiden, we've actually done one of these projects to reach the others, like the non-physicists in our city, in the city where we live in Leiden, and it's called the Wall Formula Project. Now, to introduce our topic, I have we've made a movie, so I will start that movie now. It takes 3 minutes, I think, and then afterwards, Sens-Jan will say a few more closing words on the project and on similar initiatives in other cities. It might be a bit nauseating, the movie, so sit tight and enjoy it. Let me share my screen.
In Leiden heb je meer dan 100 muurgedichten. Hier achter mij is de allereerste in het Russisch. En die gedichten zijn in allerlei talen. En mensen die hier rondlopen, toeristen, Leidenaren, kunnen daar plotseling tegenover komen te staan. En verrast worden door hoe iemand de wereld heeft beschreven in taal. Wetenschappers, natuurkundigen hebben een andere taal. Wij gebruiken de wiskunde om de natuur te beschrijven. En voor ons werd de vertaling eigenlijk van muurgedichten daarmee muurformules. En geïnspireerd hierdoor willen wij muurformules plaatsen in de stad Leiden. En ondertussen hebben we er al 8 neergezet.
Hier staan we voor een van de Leidse muurformules. Dit is een geheim dat hier in Leiden aan de natuur ontfutseld is door 2 jonge promotiestudenten. En wat aan de basis staat van heel veel belangrijke ontdekkingen en toepassingen in de natuurkunde. Nou, het idee is dat mensen hier door de stad wandelend tegenaan lopen, het per ongeluk tegenkomen in het wild, zeg maar. En zich erover gaan verwonderen en zich afvragen wat hier in Leiden allemaal gebeurt. Nou, dit gebeurt in veel meer steden in de wereld natuurlijk. Al die ontdekkingen en al die zoektocht naar de geheimen van de natuur eigenlijk. En onze hoop is dat het ook navolging gaat krijgen in andere steden in de wereld.
Dus zij komen met de formule aan en dan praten we over de inhoud waarvan ik echt geen bal begrijp. Ze beginnen op een niveau die ver boven mijn pet gaat. Uiteindelijk komen zij met de grondvorm aan en dan kijken wij of de cirkel groot of klein moet, of dat het de formule onder of boven moet, of nou noem maar op. Willem is van de typografie, dus zijn de letters in zijn ding en de beeld en kleur en vaak het totale beeld, dat komt van mij uit.
So I hope you enjoyed this little footage of the wall formulas in Leiden. And the first thing we want to do is actually to commemorate Jan Willem Bruins. As you may have seen, he passed away. He passed away last week, and today is the day of his funeral. And he has really played a very important role in the wall formulas and wall poems in Leiden, and really basically made his mark in the city by his own painting and also typography that he sometimes invented himself. So there's a bit of a negative note, unfortunately, to our presentation here, and we want to thank him for all his work. Having said that, I hope you enjoyed this movie. We made it this way to give you an impression of what it's really like to have formulas in a city, and that you can bike or walk from formula to formula. And that's something that we hope will inspire you and others to also think about science in the public domain. And we are very happy to see that already in Utrecht there are 2 wall formulas and a 3rd one coming up. And there's other towns like Groningen where there's initiatives. And what we basically hope to do is to finish our project next year when Leiden is the European City of Science. And that will also be the place where we will assemble cities from all over Europe, and we'll basically try to convince them that it would also be a wonderful idea to spread this concept. And hopefully we can finally go for wall formulas or scientific art in cities all over Europe and maybe even all over the world. So that is our goal for next year. And with this, we would like to thank you for your attention.
Thank you so much, Jan and Ivo, of course, for this amazing project. I mean, I love these things, and I hope that they will be seen in many more cities to come, because we have some sort of strange idea that there's, or not us, we physicists understand, but non-physicists don't see the beauty in formulas, and you make that a little bit more accessible. So thank you so much. There's one question in the chat who was wondering if maybe a graffiti artist is also a nice complementary approach. I think it was asked before the news of your condolence. I mean, that is besides that, of course, but.
Yeah, and I see a question of how it is funded. In our case, it is funded by the municipality of Leiden, by the university, and by the Gorter Stichting and Lorenz Fonds. But there's fortunately now also other kinds of subsidies that have become available, like KNV and MBA. And but of course, these are things outside the standard path, so you have to find your own sponsors.
Right. Thank you so much, both, and keep making those walls. And I hope that many people will follow your example. Thank you so much. And I would like now to go on with with the next part. Which is something something completely different. I would like to introduce the commissaris van de Koning, Arthur van Dijk. If he would like to join us right now, that would be wonderful. Is the commissaris van de Koning of North Holland already here?
You should see me now at the moment.
Yes. Hello, Arthur.
Goedemiddag. Can you hear me?
Yes.
No echo?
No echo.
Okay, thank you. No, it's in English?
If possible, otherwise in Dutch is also possible. It's
let's try to do it in English, Diederik. So nice to be here on your on this special occasion and the celebration centennial of the Netherlands Physical Society. It's quite an achievement, 100 years.
Thank you so much.
But probably all the people are asking, what's the Commissioner of the King doing in this celebration centennial?
I can imagine, but maybe they have some inkling, but it's.
Yeah, I'm here to of course to present a gift, and I think a special gift, because we are very proud on the society of on the Dutch Physical Society, the Netherlands Physical Society. I think it's a unique society for physicists in the Netherlands. You unite people, you bring your expertise to other people in a way that people really understand what's going on. We had further, earlier this week, we had a discussion together where we talked about this. So your organization, your society is really for a broader audience than only the experts themselves. And I think that one of the reasons why I'm here today is to stipulate that how important societies like the Netherlands Physical Society is. And that's why, and I won't take long in this meeting because, of course, you are, I think, almost in the program for a break. But I think with more than 4,000 members, the Netherlands Physical Society is a big national society. And also in Europe, there are similar societies in Germany, in the United Kingdom. And perhaps, I think, to be honest, I think that it was no surprise that after 100 years, I'm really delighted to say that His Majesty the King has honored the request to award your society with the predicate royal. And that means that from today on, the Netherlands Physical Society can call themselves royal. And how nice is that, Mr. Diederik Jekyll?
Thank you so much, Arthur van Dijk. Thank you for this. For I think personally, it's an honor. It's at least a sign that we have a long heritage. It is a process that is not many people know, but is thoroughly checked if everything is in order and there are no historical faux pas or anything. It's a certificate of excellence, and whether you are very much proud of the royal institution or not, at least we are very proud to be called royal, and that it's an honor that's bestowed upon us. And I thank you so much for giving us this on behalf of His Majesty the King, and
yes,
for joining us in this festive moment. So thank you so much.
Now I think we are going to show the real physicists our magical moment, because I'm now going to hand over you digitally, and there it is.
Yes.
So it's really there, the charter that belongs to this wonderful occasion. And I think you really have something to celebrate. And I saw already in the chat all the congratulations coming. I see them now in my screen, and I think you deserve it more. You deserve it really, and it's a precious moment for your society. And I hope that in the coming 100 years, of course, the work and the pleasure you have will be the same. So thank you very much for giving me some time and to break in your wonderful program. And I hope that that we will see each other very soon, of course, and go on with the good work.
Thank you so much. We will try to make our predecessors proud, and thank you again for the honor and for joining us. Thank you.
You're welcome. And have a nice weekend, of course.
Yes, you too. You too. It's a few hours, but we will get there. So, ladies and gentlemen, thank you, Arthur van Dijk, Commissioner of the King, and this might be a good moment for us all to get our breath back and to take a small break. And you can see there's now a small crown above keep calm and take a 5-minute break that wasn't there before for the astute viewers amongst yourselves. So next to come is, of course, the results of the Young Speaker Contest. We'll have the Nobel Prize winners, Physics Teacher of the Year, the pub quiz, and much more. It will be amazing. It will be great. Please come back in about 5 minutes and really stretch those legs and get some coffee. See you in a bit. Hello, everybody. I hope that we're all back from our small little break and that we've all caught our breath. I think it is time to go to our main speakers of the day, I might say. In 2020, the Nobel Prize in Physics was divided. As you may remember, one half was awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity, and the other half jointly to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. This year, we have the honor of having two Nobel Prize laureates here to give a talk. Due to time constraints, it won't be possible to ask questions at the end, but I hope, or we hope, that the fact that we have two, well, makes up for this. First, we start with Reinhard Genzel, a German astrophysicist, co-director of the Max Planck Institute for Extraterrestrial Physics, a professor at LMU, and an emeritus professor at the University of California, Berkeley. And Reinhard Genzel studies infrared and sub-millimeter astronomy, and he and his group are active in developing ground and space-based instruments for astronomy, and they use these to track the motions of stars at the center of the Milky Way around Sagittarius A star, and show that they are orbiting a very massive object, now known to be a black hole. Genzel is also active in the studies of the formations and evolution of galaxies. It is my privilege to give the digital floor to Reinhard Genzel.
Diederik, thank you very much. Now let me see. Let me try to share with you my slides. Okay, I hope you can see all of this. So what I will do is to describe to you a lengthy journey, actually, for me personally, but also for the scientific community in testing general relativity in a limit which really was not possible until a few years ago, and in fact experimentally show that one of the early predictions, namely the existence of black holes, of these bizarre objects, actually is a reality. Now, let's all reflect that GR is 105 years old. So it's a remarkable thing that after 105 years, the number of publications in this field is growing exponentially. And only recently, actually, has there been experimental evidence of the type which you would, as physicists, accept. So, of course, there's the fantastic theoretical work, starting with Einstein himself, the first solution by Karl Schwarzschild, showing the concept of the event horizon, also the singularity. I leave this theoretical part to Roger Penrose, who's speaking later. So I'm the experimentalist who, of course, wonders whether the predictions of the theory that there are these objects where light cannot escape, and perhaps there are singularities at their centers, actually have been realized in nature. And as you may know, it took a long time, 50 years. In fact, about the time when Roger and Roy Kerr and others started working on new aspects of the theory, when in fact the first evidence came in form of compact X-ray emitting binaries on the one hand, and objects we call now quasars on the other. The binaries we think are stellar black holes, and we'll come back to this in a minute or so. The quasars were postulated after some theoretical work to be accreting black holes, thereby using the fact that while light cannot escape from within the event horizon, you can release enormous amount of energy of gas and also stars, which are falling into the black hole and just outside of the event horizon. So for a maximum Kerr hole, about 40% of MC squared can be released, and thereby you might be able to understand these spectacular objects. That was the birth of the concept, the paradigm of massive black holes in the centers of Milky Ways. But how would you test that? How would you test that from a physics perspective? Well, you would have to go in there and send a rocket in there and measure gravity, of course. That's what we do, right? But these objects are far away. The first one, which was discovered several billions of years, and we have now objects which are basically all the way almost to the Big Bang. And so they are much too far away to do any detailed dynamical tests of gravity. But Lyndon Bell and Rees in 1971 proposed that, well, if the quasars are just sort of the special objects, special galaxies where massive black holes reside, but are accreted, maybe other galaxies, including our own, might have such black holes, only not very much accreting. And in fact, that paradigm then led to an increasing amount of activity observationally, and that included then also myself, as I will describe, and led, in the case of the Galactic Center work, by our group working with the European Southern Observatory and Andreas Gesse's group working with the Keck telescopes, to really a rather impressive set of observations over 40 years. In my case, it's been 40 years, to make a case which is now fairly sound beyond any reasonable doubt. At the same time, the objects which I mentioned as X-ray emitting binaries sometimes spiral together and emit gravitational waves. And that too has now been all of a sudden possible to measure and led to another Nobel Prize 4 years ago, 3.5 years ago, and is now a new field in astronomy. Finally, while the gravitational waves and our infrared waves are probing some aspects, the radio astronomers with intercontinental interferometry can look at the emission of short wavelengths, microwave emission at very high angular resolution, and thereby, if you like, make an image. The first such image was published 2 years ago and led to a beautiful result of as expected from GR, from a light emitting ring around a darkish region, which is interpreted to be basically the photon ring around the black hole. So that's 100 years. In the Galactic Center, this work allows us to go in particular detail because the Galactic Center is only 27,000 light years away. The problem is that you cannot work there in the optical, because between us and the Galactic Center is an enormous amount of interstellar dust, which extincts the visible radiation. But if you go to infrared waves, 4 to 10 times longer, or radio waves or X-rays, then you can look into the center. And when you do that in blue here, on a scale of a few light years, you see a very strong concentration of stars, very bright stars, remarkably so, actually. And in the middle of that region is a compact radio source, Sagittarius A star, which with radio interferometry we now know is at 1 millimeter smaller than about 40 microarc seconds. That's remarkable, 40 microarc seconds. That's about a few times the size of a euro cent coin on the moon in angle. Now it turns out that this radio source in this star cluster is also embedded in a set of streamers of gas. The pink stuff is ionized gas, and the green stuff is neutral gas. And these gas clouds move, and you can measure their Doppler motions. And in fact, that was the first experimental evidence that there might be a central mass concentration, a black hole of a few million solar masses. Charlie Towns, Nobel laureate for the invention of the meson laser in later years, went to Berkeley and moved to Berkeley and started doing astronomy. And he and his students And postdocs, and I was then one of them, used infrared equipment, infrared spectroscopy, to measure the motions of these ionized and neutral gas clouds. And they moved obviously so fast that it required a mass of a few million solar masses in the central few light years. Now, you don't know whether that must be a black hole. It could be one. How would you find out about it? Well, you have to remember Kepler's laws, right? If there is a point mass in the center of a region, like in the solar system, then the motions of test particles around it depend with 1/1 square root of the radius. So if you go further out, the motions are slower. And indeed, in the innermost region, we could show that to be true, but then you go outside of a few light years and the mass, the implied mass, increases again, which is basically the stars. So this was the first evidence. Now, is that a black hole? Well, a few million solar masses is a pretty impressive number, but at about a light year or so, you're still a million Schwarzschild radii away from what would be a black hole. So you cannot be sure. And so the work of both groups who then started working on this involved over these many years lots of continuous improvement on new technologies. For instance, low noise infrared imaging detectors, which at the time when we started in the 1980s was not available. Then the technique of adaptive optics, where if you observe on the ground a distant star or the galactic center, then the Earth atmosphere, of course, distorts the wavefronts. Now you could, of course, bring a telescope out in space, like the Space Telescope, but that's too small for our work. Instead, we are analyzing the wavefronts by looking at a bright star in the field and then using a deformable mirror inside of our equipment to straighten the wavefronts out and thereby correcting the distortions with what we now call adaptive optics. All modern telescopes are now equipped with adaptive optics. Sometimes actually there's no bright star, and so then you actually have to bring your star, make your star, by shooting laser light into the upper atmosphere, focus it there, and use resonant backscattering by sodium atoms up there to generate an artificial star. In summary, I mean, I just want to give you the feeling that, you know, it took 40 years to come to a sort of not a final result, but anyhow, a very strong result, because we had to continuously improve the technology, get better detectors, bigger telescopes, adaptive optics, and as you will see, we even now are using the combination of telescopes to interferometry. Then you have to wait and see whether you can measure the motions of the stars, for instance, on the sky. And here, this is a little movie. And so you observe over years to see these motions. It's actually remarkable. In astronomy, usually you cannot see motions directly because typically things are too far away. Not so here in the galactic center. And so you see these motions, and when you analyze these motions, then actually you see that they are parts of orbits. In fact, in one case, one star, we are lucky. Nature has given us a star which is on a highly elliptical orbit within a period of about 16 years, which penetrates at its closest to the radio source Sergei star to about 3 times the orbital radius of Neptune. It moves there with about 2.6% the speed of light, 7,600 kilometers per second. So if you take Newton's laws and calculate what V squared over R over G is, well, we'll find it's a few million solar masses. So the same mass we had seen earlier, 10 years earlier with the gas, but now much, much closer in. So this Perry approach is about 1,000 Schwarzschild radii. But must it be a black hole? Well, it's pretty plausibly a black hole, but we really need to get closer in, and our analysis of that this might be a black hole very much relies on the assumption that general relativity holds in this regime. Of course, we knew the first Perry was in 2002. We knew that the star would come back. in 2018. And so our group then worked with ESO to develop a combination of all the 4 8-meter telescopes on Parnell Mountain. You see them there, and bring the light together from each of the telescopes in an underground tunnel system, correcting the wavefronts, etc., etc. I don't have time to get into the experimental details, to build a machine which then can effectively have the resolution of a 130-meter diameter telescope. So that is milli-arc second resolution, and we can measure with a precision of 10 to 50 micro-arc seconds. So right at the scale of the event horizon and a little above. So that allows us then, with this machine, which we call Gravity, built by a fantastic team headed by Frank Eisenhower, a European team. That allowed us then, when the star came back in 2018, to measure its motion from night to night during the Perry approach. You see the green points are the positions of the star. The black hole is the black circle. And the closest approach happened in May 2018. And I mentioned already the motion there is about 2.6% the speed of light. So what did we see? Well, we saw indeed a number of the effects of general relativity. For once, the so-called gravitational redshift, which is basically the clocks are going slower in strong gravity fields. So if you plot the Doppler motion residuals of the motion of the star, then because of that shift,
Oh, Mr. Gensel, your microphone is on mute.
Okay, I don't know how that happened.
Thank you so much.
It's all right. That's bad. So you see then, if you compare the motion on the left side there of the star in these red dots relative to the Newton orbit, which is the gray line at 0, you see very clearly the deviations, exactly how general relativity predicts, which is what the blue line is. So this is a very significant detection of the gravitational redshift. Another effect which theory of Einstein predicts, of course, is that the star orbiting a point mass or a compact mass does not move on a closed ellipse, but on a prograde precessing ellipse. Now, for such a highly elliptical precession, that precession is more like a kink in the orbit. And in fact, down below, you see on the left side, the residuals, again, between the Newton orbit, which is the vertical, the horizontal dashed line, and the observed motion, and red is what general relativity predicts with the Schwarzschild precession. So clearly we have seen the Schwarzschild precession, which in this case on the sky is an angle of 12 arc minutes. So that's much more than the famous experiment which was done to show the precession of Mercury and gave Einstein the great first success and experimental confirmation. The last thing we've seen is in fact motion of gas, very hot gas, very close in at about 5 to 10 times the gravitational radii, where the gas clouds move with 30% of the speed of light. And indeed, that's about what the coordinate speed should be if general relativity holds. So we have very good evidence that this object really is a black hole. Now, of course, let me ask, must it be one? Okay, must it be one? Why has the Nobel Committee said for the detection of a supermassive object and not about supermassive black hole? And the answer, of course, is we are not done yet. We need to go further, measure the spin of the black hole, and show that the no-hair theorem is correct. So that's sort of our business plan for the next years. In the meantime, the situation is such that we've proven where we knew 40 years ago that there was a few million solar mass object within about 10 to the 6 Schwarzschild radii. Now we know that the same mass is there within about 10 Schwarzschild radii. We know that any extended mass inside the orbit of S2 is less than a few thousand solar masses. So there are likely some stellar black holes and stars there, which you're trying to see in order to measure the spin. And any partner of the big black hole, for instance, people speculate that there might be either a binary or an intermediate mass black hole, would have to be less than about 1,000 solar masses. So we can use these measurements now to actually test in detail the astrophysics of a star cluster in such an extreme environment also. So there is the astrophysical part of this work, as well as the physics, which I mentioned to you. Okay, so I guess I'm out of time. So this has been a long but extremely rewarding journey. You might imagine that many people had to work on this over these 40 years, and I'm very grateful to a large team of young and not so young people who've been doing this. And I'm also grateful to the international European collaboration, which really made this all possible at ESO. Thank you very much.
Thank you. Thank you so much, Professor Gensel. We will, of course, send you a small token of our gratitude, our specially engraved glass. But thank you so much for showing us your amazing work and that of your team, and finding this supermassive object and making it plausible, at least, that it's a black hole, and measuring the effects on general relativity in the orbit and the motion of gas. And it's really amazing work. And I hope you won't find any hairs then the next couple of years, and good luck with all the astrophysical measurements that need to be done. Thank you so much for being here.
Thank you.
And well, we've heard from one Nobel Prize laureate about black holes, and now we will hear from another. Sir Roger Penrose is a mathematical physicist, mathematician, philosopher of science, and, well, Nobel laureate. And he is Emeritus Rouse Ball Professor of Mathematics at the University of Oxford, an Emeritus Fellow at Wadham College, Oxford, and an Honorary Fellow of St. John's College, Cambridge, and University College London. He made contribution to the mathematical physics of general relativity and cosmology. He has received many prizes and awards, including the 1988 Wolf Prize in Physics, which he shared with Stephen Hawking for the Penrose-Hawking singularity theorems. And there are many contributions in different fields that he made, and we're honored to have him here. So if you are already here, Professor Penrose, I would like to give the floor to you.
Can you hear me?
Yes, loud and clear.
Can you see me?
As seen as well.
Good, thank you. I hope that's clear enough. And I hope to get my PowerPoint pictures on as well. How does that work? I've done share screen, and then I'm sort of baffled because I see all sorts of things. Where would it be?
In this list, there should be one with the PowerPoint logo.
No, I can't see these things, unfortunately. Where would that be? It's not that one, I guess. Let's see it. I've got my PowerPoint. Oh, here, that's probably it. Can you see anything?
Not yet. If you press share on the down right corner.
Done share. Oh, down right corner, sorry.
Yes.
Share, yes, okay. So as long as I get the right one of those pictures, and I can't see any of them, but let's hope this is correct. No, that's not correct. Oh. How do I get my PowerPoint up there?
Slightly to the right.
Just a minute. I've lost the picture, sorry. I'm an incompetent when it comes to these things. Unfortunately, you have to bear with me.
Well, if you calculate black holes, then other people are better at information.
Well, I can see my picture, but you can't, I guess. No, how do we do?
we can see the picture if you put it on full screen.
Oh. Good. So can you, this is, the main picture there is the picture in my paper, which apparently got me eventually a Nobel Prize. Can you see that picture?
Yes, but if you could maybe put it on presentation mode, then it's more full screen.
Yes, I realize this is something I've not learned how to do. Where would I find that on the screen?
I think in
slideshow on the top.
On the top corner, yes, the top
The
slide.
third from right. View, review, slideshow.
Third from right at the top. Share screen.
Now inside the PowerPoint, underneath the red bar of PowerPoint.
Red bar of PowerPoint. Yes.
There it says slideshow on the slightly above and to the left, to left, to left, to left.
On the
left. More left.
More left.
More left. More left.
More
More
left.
left.
Stop.
There.
Slideshow.
Slideshow. Okay. Do you see it properly?
And almost slightly down and
slightly down. What the pinky, the
function key 5 is worth a try.
Sorry?
Function key 5 starts the slideshow.
Key 5. Oh dear. Now how do I find that? See, I have an additional, apart from being incompetent, I have bad eyesight.
Function key 5.
No,
F5, yes.
F5. F5. I just pressed it. What does that do? Does that do something?
No, that didn't work. So we go back to slideshow. And from slideshow, you get a new list of options and you have to take the up.
There is slideshow at the top.
Otherwise, Mr. Penrose, we can see it. It's slightly smaller. We can see your desktop if that's all right for you as well. Then we are more than interested just to hear what.
Why don't I do it like this? Because I shall spend too much time trying to explain.
This works wonderfully.
Let's do it like this. Okay, well, here we have the picture which appeared in the paper, which eventually seemed to have got me a Nobel Prize. This represents a gravitational collapse in the spherical symmetrical case, but I want to show that if you perturb it, you still get a singularity in the middle. And this ring that you see in the middle, you have to imagine there's another dimension. So what looks like a ring is really a sphere. And the point about it is that if you have a flash of light on that sphere, then the light from it is converging. The inward and the outward light flash would be both converging. And this is an unusual thing to have something which is compact and has this converging property. And this was the criterion that I used. It's called a trapped surface. And once you get that, then you can prove a theorem which shows that something goes wrong. Basically, that you get a singularity. In fact, you start off from a surface which is non-compact, which is your initial data surface. And then you get the future of this trapped surface you can show has to be compact. And this leads you to a contradiction. I won't go into the details of that. That's not appropriate here. But I do want to explain the important thing about these pictures is the light cone. And of course, here we have the four-dimensional space-time, 3 space axis and 1 time axis. And the light ray is what you have to gauge things so that if time is in seconds, then the distances are in light seconds, so that the light ray is more or less at 45 degrees. But that's just to get it so that it looks reasonable. Okay, let's go back to the general collapse picture. And here we have the horizon and a singularity, which is likely to be much more complicated than that in the middle. Now, when I had this theorem, I gave a talk in Cambridge. I gave one in London first, and then one in Cambridge, and Stephen was present at the second one. And Dennis Sharma arranged that we got to speak together, and I explained the techniques that I was using to Stephen and to George Ellis, I believe, at the same time. And then Stephen picked up on them very quickly and started to apply these ideas to cosmology. So the idea was, well, first of all, before getting into that, let's suppose we have a collapsing universe. You see, suppose we have a universe which time is going up in my pictures normally, and instead of having a nice, simple singularity, which you might expect to see when you have lots and lots of black holes and they all start to congeal with each other, you get one great mess in the end. And it's characterized by the fact that the Weyl curvature, that's the conformal part of the space-time curvature, and that blows up and becomes horrendously infinite. Anyway, so that's the picture we get for a general collapse. But what about for the situation, more or less what we see in our universe? We see an expansion. Well, we also have this exponential expansion, which plays an important role in what I want to say shortly. But the general picture, of course, the universe might be closed or it might be open. That doesn't play any role in what I want to say. So I've indicated at the back that it might go on forever or it might close up. I don't care for the point of view of this talk. But we do have this Big Bang, which is a singular state. People try to introduce this notion of inflation, which doesn't make any difference to the discussion I want to make. The problem is that why do we not get a situation like this, which is the time reverse of the sort of thing we saw before? A generic singularity would be have these enormously diverging Weyl curvature and very complicated situation. So the real problem, which I began to worry about, is why is the universe like this and not like this? Why don't we have a very complicated initial state? And the argument I was putting forward, if you can put inflation into it as well, it doesn't make any difference because you put your inflaton fields in or whatever you like, and it makes no difference, no essential difference to the collapse being this great mess. And you can see that working up using the Bekenstein-Hawking formula for the entropy, you can see how improbable a situation like this, and it's something like 10 to the power 124, figures like that. So it's ridiculously improbable that the universe was like this. I want to stress this point in a different way. I'm imagining now, this is the top three pictures indicate a gas in a box, and I imagine that this gas is initially in one corner. You open up the box and the gas spreads out throughout the box. So time going from left to right, entropy going from left to right. Entropy is increasing in this situation. Now the bottom two pictures, I'm imagining a galactic scale box with lots of stars in it. And then time still going from left to right, and the entropy definitely going from left to right. You get clumping and you get finally things like black holes. So the entropy shoots up by an enormous factor when you get black holes. So what we find in our universe, this is what's rather remarkable. It's not just that we have low entropy in the early universe, but we have low entropy specifically in gravity, because we see uniformity, and this uniformity is consistent with the gas being uniform or whatever. In fact, we see by looking at the cosmic microwave background, there's this beautiful Planck curve for the temperature spectrum, which tells us that it is, as far as the matter and the radiation is concerned, something at a maximum, essentially maximum entropy, whereas gravity is essentially minimum entropy. So we have to explain why it is that gravity is so special, or what it is that well, what I want to do is to move to a different way of looking at space-time. And this, well, it's mainly saying that what's important in the structure is the light cones, and that's all. The null cone at each point is the structure, and this is the conformal structure of space-time. Now, it's very useful to think of conformal structure, and we see this illustrated in this beautiful picture by the Dutch artist M.C. Escher, where you have infinity represented. This happens to be a picture of the hyperbolic space. This is the Beltrami or Beltrami-Poincaré disk. And we have the Escher picture of these fish creatures. One thing I would point out is they have eyes which are exact circles, and they remain exact circles right up to the edge, which is illustrating the conformal nature of this picture. That when they get squashed down, they get squashed down equally in all directions. And so small shapes are preserved, and in particular, small circles are preserved. And this means that you have a conformal picture. But in this picture, that you can represent infinity, which is what I want to use this diagram for, just to show you that with a conformal description, you can represent infinity as in this case, which is a perfectly smooth boundary. And you could imagine extending to something outside the boundary. That's there would be no contradiction with the conformal structure by doing that. Okay, as I said before, it means the light cones. Now, I want to talk about the whole universe now. And it's a feature of having a cosmological constant, which seems to be the case from the observations made in the, the turn of the century, basically, and that also a Nobel Prize for the 3 main people concerned with this. And what they find is something like, well, people call it dark energy. I don't like the term because it's neither dark nor energy. It's transparent, and it's certainly not like energy because it's repulsive rather than attractive. So it's something quite different. It's the cosmological constant or something very much like a cosmological constant. But the feature of this is that the future infinity is space-like. So it's like a time, it's time infinity, if you like. But as far as the causal or the conformal structure is concerned, it's a space-like structure. So we can squash it down, and this is what I've done in this picture, to be space-like. Now, what about the other end? Now, you can, in the models of cosmology that we see with the Big Bang, they pretty well have the feature that you can stretch them out also to make a smooth boundary. But it's quite different because in general, the future, well, if it were a collapsing situation, you would expect to get diverging Weyl curvature and something completely wild. But what we get is something very different. And well, people used to say, well, how do you deal with the singularities? What you have to do is to bring quantum mechanics in, and there's a theory of quantum gravity. And I used to think this too, like everybody else. But then I began to wonder, it must be a very peculiar theory, because if it has the effect of dealing with the singularities in the future, why does it give you a completely different answer for the singularity in the past? Something very, very smooth, something for which the Weyl curvature seems to vanish as opposed to diverging wildly to infinity. It's almost the opposite. So what kind of a quantum gravity could give you that? My answer to this is it's not quantum gravity. It's something where you have to look at it from a conformal perspective. And in the smoothed out models, you can stretch it out and make a nice boundary like this. But what about in general? Well, this was really my student, Paul Todd, who suggested that this would be, and he didn't just suggest it, he worked at it and worked out equations and so forth to what happens in a general case where you have a smooth boundary, which could continue to something beyond, but this is just a hypothesis. You don't say it should continue to anything behind it. You just say that the condition is that it would be smooth enough so there would be a conformal extension if you wanted to have one. But the idea going beyond that is to take it seriously as physics. Now, this is the next step. So what I want to say is it's not just a neat trick, but it's something which is serious physics. More than that, it's something, now this is what's outrageous. Up to this point, I've not said anything which is outrageous, unless you think not believing in inflation is outrageous. But I think inflation doesn't answer the question. You have to have something else. And what I'm saying is that Paul Todd's idea of making it smooth is part of the story. The rest of the story is to say that the Big Bang was the continuation of a previous eon, as I'm calling it. These each steps here are what I call eons. Our eon started with the Big Bang. It's finished in a certain sense at infinity, but in the conformal sense, it finished at this conformal boundary. Now, how can I get away with joining them together? Well, you see, when you have a very cold and rarefied situation, when you squash it down, it becomes hotter. What about a very hot and dense situation? When you stretch it out conformally, it becomes colder. And it's sort of not unreasonable that it should match. Now, it's only reasonable physically it should match if you have the case that the physics is basically free of matter. So you can imagine it has to be zero mass fields. Well, in the remote future, it's dominated. The particles are mainly photons, but it's not quite the whole answer because you do have some other particles. You have hydrogen and things like that. And so I have a hypothesis, which is that the mass fades out in the remote future. One can justify this on certain grounds, which I don't want to go into here. But that's a hypothesis that the mass does fade out in the remote future. What about the Big Bang? Well, there it's easier, because in the Big Bang, things are so energetic that the mass becomes completely irrelevant. The energy in particles is almost completely dominated by their motion and not by their rest mass. And so in effect, the closer you get to the Big Bang, the more and more massless particles are. And so the argument is that in the limit, as you go into the past, things become massless. Into the future, they become massless. And therefore, the physics is the physics of massless particles, and conformal geometry makes a lot of sense in that case. Okay, what about observations? Because this is all right for a hypothesis. I used to think, well, nobody will ever prove me wrong, and so therefore I can talk about this forever. But then I started to think, well, things can get across. So let's indicate this. Photons can certainly get across in principle. If they are long enough wavelength, they could actually get through. And I want to say a bit more about that in a moment. I don't know how much time I have left. It's probably negative, but I hope I can still say a few things. I did wonder about observational tests, and here I have one of them. You must imagine that, well, we had a nice description of a black hole in the center of our galaxy, very impressive indeed. And there is also a black hole in the Andromeda galaxy, a much bigger one apparently. And eventually, not too long, I suppose in the future, in the scale of things, we will collide with the Andromeda galaxy, and eventually our black holes will feel each other out and spiral into each other. And when they collide into each other, we more or less get swallowed by the Andromeda one, which is much bigger, but there will be gravitational radiation coming out from this. Now, in a galactic cluster, there will be many black holes in the different galaxies, and as they come together, they will get bigger and bigger black holes, and you will have eventually several of these collisions, which will send signals out. So in this picture, I'm showing you, this is a cartoon of the crossover, the surface in the middle, the sort of rectangular thing there, is representing the three-dimensional surface, which is the crossover surface from the previous eon to our eon. This is us at the top looking back, our past light cone, and these are several explosions as the black holes encounter each other, and the explosions in the form of gravitational waves, which will come up and in a sense come through, and the signals will be registered on our microwave background. They will be very faint. I've deliberately drawn them at the bottom as these sort of rings, which we'd see, but deliberately faintly because they're very faint. But they are there, the claim is, and you will see them with having lower variance in the temperature than most other places. So my Armenian colleague Vahi Gursajan looked for triples of rings which had unusually low variance, but you had to have three concentric ones to get a significant signal. And what did he find? Well, in the Planck data, what he found was the following. This is the centers of these triples of rings. And what's remarkable about it, as far as I'm concerned, is the clumping you see. You see them in three or just rather small number of pretty big regions, but not spreading over the whole sky. What's more remarkable, I should point out that these central three regions here are excluded, so that they stop off there merely because you don't look there. But the centers of these rings are also clumped in color as opposed to just their angular distribution. Color means, well, just means temperature, and red means high, well, it means higher temperature. It really means blue shifted. So you might think they're more distant, but when you look at the details of the theory, it really means that they're distant. So the red ones are the distant ones according to the theory. And the fact that they're clumped in color means that they are also clumped in their distance from us, not just in the angular distance. So I find this very, very striking that you do have this clumpiness. And if you have another theory which explains these features, I'd like to see it. But it's certainly explained by the cosmological model I'm putting forward, CCC, because, well, it's explained if you believe that there are large regions which are not necessarily super duper clustered, I would say. Okay, that's one piece of observation. Another one is the result of black holes in the remote future. Hawking evaporation will eventually make them disappear, and there will be, all the mass will be concentrated in the radiation, apart from what happens to the eventual singularity here. But this, as you do the conformal squashing, since this happens so late in the universe's history, something like 10 to the 100 years for the very biggest ones, they will be squashed into a single point on the crossover surface. So here I have a picture from a paper written by myself and Christoph Meisner, Daniel Ann, and Pavel Mirovsky. And it was the analysis done according to a screen by Christoph Meisner, and the detailed analysis was looked at by Daniel Ann. And what they find is, according to this analysis, there are points. Let me see what you would expect to see on the theory. This bottom horizontal line is the crossover from one eon to the next. So this is the previous eon, and above that line is us. The Hawking point, I'm calling it, that is all the radiation and everything that might be left of the black hole is concentrated, because it happens so late, into a tiny little point. So on the other side, it would be a tiny point which is even smaller than the Planck scale. So very, very tiny. But you don't see that because the radiation from it just scatters. And certainly from the work of Jim Peebles and other people, you have a good feeling for what happens here. And 380,000 years, it scatters around and you don't see anything until decoupling and things like this happen, and eventually you can see the radiation coming out. So the Hawking point will then spread out to this region, which is about 4 degrees in the sky, which is about 8 times the diameter of the full moon. So these spots will be, roughly speaking, because all the scattering, be something like a Gaussian distribution, and they will be heated in the middle and cooler as you get to the edge. Maybe for the strongest one, something like a factor of 30 bigger than the normal variations in temperature. You might ask why these things have never been seen before. I think the answer is that just nobody has looked, because they believe, because of inflation and all that, that somehow the cosmic microwave background should be not producing signals like this. But according to the analysis, the significance of the presence of these signals is 99.98% confidence level. Not only that, but the 6 strongest points, well, I should say the 5 strongest ones in the Planck data are also seen in exactly the same places in the WMAP data. You look in the WMAP data and you find another very strong point, and that's also seen at the same place in the Planck data. So those 6 points I consider to be pretty genuine candidates for Hawking points, and they would be if, well, I mean, the theory predicts them, and I don't know of any other theory that predicts them. I would like to see these things analyzed further to see how strong the case really is. Certainly the 99.98% confidence level strike me as something that means you should take them very seriously. Thank you very much.
Thank you so much, Professor Penrose, for your great presentation on the space-time singularities, black holes, cosmology, the fading mass in the future, and the Big Bang. Thank you for taking us from eon to eon and your cosmological model. And we send you, of course, our inscribed glass, and I am sure that I speak on behalf of everyone. Our sincerest thanks for your presentation.
Thank you.
Thank you so much. Then I would like to continue. It's normally a tradition at FYSICA that we visit different universities each year, and that is always interesting to see other places and how they do things. This year, due to Corona, it's not possible, but Professor Steven Hoekstra has a solution. He works at the Rijksuniversiteit Groningen, and he will give us a virtual lab tour so we can visit Groningen during these trying times. Steven, I hope you are with us.
Yes, I am. Let me switch on my devices and share the screen with you. One moment. There we go. I hope you see your first slide, Diederik. Yes. That's working. All right, very good. Yeah, so I'm honored to give you a kind of view into our kitchen to look a little bit at what the experiments are looking. I normally always really like to go on a lab tour because you well, you meet the people that actually do the work, right? That are hands-on on their experiments, and that's also what we'd like to show you today. So I represent a research program that we do with a whole team, both in Groningen, like was mentioned, but also at the Vrije Universiteit Amsterdam. And actually our whole project is part of NICEF, the particle physics organization in the Netherlands. So before diving into the lab, I need to give you a short introduction to what it is that we're doing actually. So I need to tell you about the electron EDM. It's the electric dipole moment of the electron that I'm talking about. And the question is, can we measure this electric dipole moment of the electron? And so on the picture you see on this slide, you see this fundamental particle, the electron, that in principle does not have much substructure, could actually get an electric dipole moment through interactions with standard model particles, but even beyond the standard model particles. And the magnitude of this electric dipole moment that it would acquire depends on the structure and all the particles that are out there. For that reason, measuring this property of the electron is a good way to test the standard model of particle physics. However, we don't do experiments on bare electrons. We actually use a trick, and that is to have a molecule. Like here you see a polar molecule, just two atoms together. The atoms are not the same. And inside this molecule, you get a hugely amplified electric field. And this large electric field we can use to explore the properties of the electron. So the key thing is, by measuring something on the molecule, you can learn about the electron. And this enhancement is about a factor million. It's really gigantic. So with this idea in mind, we started a program for a number of years now to exploit these properties of molecules and actually make a molecular beam, a very intense molecular beam, in our case of barium fluoride molecules, where they fly from the left to the right. Well, I don't really want to talk too much about the details here. There's also no time for that, and I would like to actually give the stage to the students that actually do all of the work here. I would just like to show that this idea of making this experiment, we of course need to translate into a machine. We call this tabletop particle physics. It's about a 8-meter long table, so plenty of people can join. And we also need a kind of a good team of people with expertise from particle physics to molecular physics to optical physics and magnetic shielding. So I would like to introduce mainly this team of people. These are the PhD students that are working on our project in recent years, and they will take you to the lab and tell you and show you what they're doing in the movie that I hope will run now without any technical issues. So here we go.
Hello everyone, my name is Maarten Mooi and I'm working here at the VU in Amsterdam on optimizing the molecular source for the electron EDM project, which we do together with the University of Groningen and NNV. I'll show the key elements and hopefully you get some idea of how my life in the lab looks. So first of all, we work with vacuum, so we have vacuum chambers here, and you're lucky as we opened the vacuum here and pulled out this top part, so we can reach the parts which are normally inside the vacuum. We can easily reach now and operate. Now, we make barium fluoride molecules by a reaction with a barium target, where from this target we ablate barium atoms by an ablation laser. Hopefully my camera can record it. As it's a few nanosecond pulses, my camera sometimes has difficulty with it. And we let those atoms ablated from the target react with SF6 gas and to form barium fluoride molecules. These molecules are hot and fly in all directions due to the ablation and the reaction. But we do this inside the cell, and this cell is 20 Kelvin, and through this cell continuous neon atoms flow. And therefore the barium fluoride molecules will collide with the neon atoms and thermalize to the 20 Kelvin of the neon gas, and will be extracted in this neon gas outside the cell. It's good to make the beam. We want to optimize it, but to optimize it we need to detect it. and I will show you briefly how we detect our molecules. We do it by resonant absorption. For this we have a laser, which is titanium sapphire laser, that red light pumped by a green laser, and with this optica we make multiple beams of it, put it in optical fibers, and also reduce intensities and polarization control. And so if we then look in time, we see our absorption laser, we measure the intensity, and now if there's an ablation, some time later barium fluoride molecules fly through the absorption laser and will absorb some light. And this leads to some extinction, and we can detect our molecules. This is all very state selective, so we know exactly the internal behavior of the barium fluoride molecules. So with this source, we want to optimize our source, make as much as possible barium fluoride molecules. And now you go to Groningen and see what you can do with those molecules.
Hi, I'm Hanno. I'm also part of the NL-EDM collaboration. Here in Groningen we also have a cryogenic source, like the one Maarten has in Amsterdam. Here we have the Stark decelerator behind it. So for a Stark decelerator we need high voltages. And these are in these amplifiers. So we have 8 amplifier boxes, since we have the Stark decelerator of 8 different electrodes. In this 4.5 meter long record holding Stark decelerator, we have 9 modules. The modules look like this. So this is a picture of 2 modules, and in the modules there's 8 rod electrodes, all with many ring electrodes attached. So if you zoom in, you see that here there's the 1, 2, 3, 4, 5, 6, 7, 8 rod electrodes with many small ring electrodes. Here standing below is one of the rod electrodes. So here you see the tiny little rings where the molecules fly through. To such a rod we apply an electric field, and as there is 8 of these intersecting into each other, and we apply different voltages to subsequent rod electrodes, we get an electric field shaped like this. So you see that there's traps formed, and in these traps the molecules are confined, and by switching now the voltages on the different electrodes, we can tune the velocity with which they fly through, and therefore also decelerate them. You can also see these rings at the end of the decelerator, so we'll show you now. So here you see the 8 rod electrodes with the rings in the middle. This is 4.5 meter of small rings all the way to the cryogenic source.
Hello everyone, my name is Parul. I'm also a PhD student in the NL-EDM collaboration. So as Anu told you about the operating principle of the Stark decelerator, in this part I will tell you about the way in which we detect the molecules. So here you see an optics assembly through which we send a laser at a specific wavelength inside the chamber at right angles to the molecular beam propagation. This laser excites the molecules from an electronic ground state to an electronic excited state. The molecules immediately decay back to the ground state, and in this process they emit fluorescence. We collect this fluorescence with the help of a photomultiplier tube. The electrical signals from this photomultiplier tube are then processed to generate a typical time of flight profile signal for the molecular beam traveling through a Stark decelerator. So here you can see some results as to how the time of flight for the molecules look. If you look at the graph at the very bottom, you can see these sharp peaks which correspond to the molecules which are in the traps of the decelerator, which you saw in the animation before. So here we have applied only a very small deceleration strength to the molecules. We can also apply very high deceleration strength to the molecules inside the decelerator. So in the signal that you see at the top, we can even decelerate the molecules down to 10 meters per second. Recently, we even trapped the molecules inside the decelerator, which can be held inside the decelerator for different times. So if I zoom into one of these peaks, you can see that these typical trapping signals consist of multiple peak substructure. This corresponds to the molecules which are sitting in individual traps inside the decelerator. And since these traps just propagate along the length of the decelerator, you detect them whenever they interact with the laser beam that we send in along the chamber. So from here on, I would finish this part. So these are the results that we got. And now P from our group will talk about the contribution of theory to the whole NNEDM collaboration.
Yes, so my name is P and I'm part of the theory group of the EDM collaboration. So I briefly want to explain you why in fact we need a theory group in an otherwise mainly experimental collaboration. So you know that we want to measure the electric dipole moment of the electron. And this is predicted by the standard model, but also by extensions of the standard model, which include more CP violation and which therefore predict a larger electron EDM. However, as you've been told in the lab tour, in fact we study barium fluoride molecules. So what we are measuring is not directly the electron EDM, but it's a molecular electric dipole moment, CP violating molecular EDM, and in our case in barium fluoride. And this is already interesting in itself, but what makes it more interesting is if we can connect this molecular dipole moment to the electron EDM. And what makes it more complicated is that actually there is also another CP violating interaction which contributes to this molecular dipole moment, so we also need to take this into account in our analysis. So really the simplest way that we can describe the experiment is that we measure an energy shift which is proportional to the electron EDM and to this electron-nucleon interaction. And these two interactions, they are enhanced in a barium fluoride. This is why we use barium fluoride. And these two, WD and WS, these we call relativistic enhancement factors. These are purely relativistic effects. And these enhancement factors are crucial for the interpretation of the measurement, but they cannot be measured. So they have to be calculated. And we use molecular electronic structure theory, which is large numerical calculations performed on supercomputers. And there are kind of three aspects of these calculations. And the first one is the basis set. This is really how we build our molecule, the molecular orbitals. Then there's electron correlation, and this is because we treat all the electrons in the barium fluoride molecule. That's 65 electrons, and we also treat their interactions. And then it's relativistic effects. I said these were purely relativistic enhancement factors, so everything has to be done in a relativistic framework. And if we do this well, we reach uncertainties below 5%. And this is, for now, sufficient to interpret the measurements. So this is what we do.
Hello, I'm Thomas Meijknecht, and this big barrel is a mu metal magnetic shield with, on the inside, the smallest magnetic field in the Netherlands. Possibly more important, it also has the most homogeneous magnetic field in the Netherlands. This is critical for our experiment, which is the search for an electron-electric dipole moment. This shield actually arrived today, and we also want to ship it to the lab to combine it with the rest of the already existing experiment.
Hello, I'm Ginny Marshall, and this is the lab where we're setting up some of our experiments. We start off with our supersonic source, which creates molecules that in a really narrow and fast beam that travels through the experiment. It's really important for us to create a well-defined quantum superposition state, and to do that we we need to use lasers. So we have lasers in a different lab, and we deliver the light from those lasers using optical fibers. It's also really important for us to control the magnetic and electric field in our experiment. So the molecules start at the supersonic source over here, and they pass through the experiment, interacting with the laser beams and the magnetic and electric fields in various forms, until finally they pass through into the magnetic shield at 600 meters a second.
All right, that ended slightly abruptly, but I think you're still here. There was one slide that was skipped really quickly. I hope you enjoyed this kind of view into our labs. And I would say, of course, if you have questions, I'm happy to answer them in the chat, or also some of the PhD students that are here as well. So with that, I think it's back to you, Diederik.
Thank you so much, Steven, and thank you for showing us your lab and the recent footage from just 2 days ago that was in there. So it's really like we're smack dam in the research itself, and it's very nice to see the group effort, as we all, as physicists, all know how it goes, and that you're only as good as the work that everybody does, and it's a team effort, and it's amazing to see. So thank you so much,
of course,
for showing us around. And yes, we quickly continue. Yes. So yes, some things never change. We do this work without being paid, of course, because it's something that we believe in, and it's important for our country. And there's so many people for the NNV working and doing this. That has been always the same, because people need some reimbursement. This is a wonderful letter from the city of Enschede, which gave 50 guilders for travel expenses. And also this is where they decided that the annual amount of money for the NNV contribution should be 250 guilders. That has changed slightly, but still, if you enjoyed this free conference, at the end we would like to send you an email with some tickies. That has changed a little bit since 100 years ago. Then they did it slightly different, and we would love, if it's possible at all, if you could do something and give us something because of the costs that we made, and so that we can keep on doing the work that we do and make physics in the Netherlands better. And even a small token of appreciation really helps to keep doing these things. So thank you so much. Another thing that is always the same throughout the century is the NNV's effort to better education. And this is, for instance, a letter in 1929 where people from the NNV try to figure out what try to sort of standardize the education, the physics education in the Netherlands, and make it more the same and of higher quality. And we're doing exactly these things right now with curriculum and new educational things, even up to the Tweede Kamer, to the government, where we try to do our part. One other thing that we do when it comes to physics education in secondary schools is choose the physics teacher of the year. And for this, I give the floor to Christa again, who will tell us who the physics teacher of the year is.
Yeah, and as we all know, I think a teacher is incredibly important in our journey, especially when we make our first steps into physics. So in that sense, I really am very happy that we give out this award every year. And the jury of this year's contest was very impressed by the shortlist of the 3 excellent candidates. That was one of these candidates was Onne van Sloten for the sparkle and enthusiasm for physics that he brings to his lessons. Kathy Baars of the Martinus College, who's always has time for her students, no matter how busy her workload is. But The winner proves to be an authentic and hyper-energetic person, a driving force behind many great initiatives, and an accomplished ukulele player, as the jury tells us. But this winner combines all we seek in a physics teacher of the year. It's a driven teacher, he has excellent teaching, he's cherished by students and co-workers, and he's contributing a lot to the community. So without hesitance, the jury has chosen Arjan van der Meij from the Populier in The Hague as this year's physics teacher of the year. I don't know if Arjan is in, so he can say hooray.
Hello.
Both say hooray. Hi, Arjan.
Hi, sorry. Okay, no, well, it's going. Yes. Thank you. Very honored to be the physics teacher of the year in centennial year. Thank you very much. And well, yeah, we're in the classroom now with many colleagues. And I see Diederik is very anxious to go further with the program because he is afraid that we will run out of time. But please give me 1 minute to thank everybody and to say something. Is that okay, Diederik?
Arjan, I've known you at least via Twitter for 10 years, so I can.
Yes. Thank you very much. I would like to say it's a great honor to be the physics teacher of the year, of course, in the centennial year. And I'll keep it short because most words of thanks are very boring. I want you to do one thing, no, two things the next 100 years. First is try to make one theory of the quantum mechanics and general relativity, because that's what we want. And the second thing is, close to my heart, find me colleagues, because remember that Hendrik Lorentz, one of the founding fathers, and also Professor Haas was also a teacher on the what we call HBS. And nowadays the influx of teachers is very low, just a fraction of the outflux of teachers. So you can help. You can find those teachers for us and send them to us, founders, gifters, teachers, and consider that a gift to our centenarian. Thank you very much and be safe. Thank you.
Thank you. We will definitely try to do so. In our ongoing struggle. Yes.
Okay.
Gista. Yeah, because we have one last prize left. Earlier today, we were inspired by a lot of young speakers, and we had a little vote. I know it was a very tight race, but the winner of the Young Speaker Contest this year is Thijs van Eden. Congratulations. As you already spoke a lot, I think we leave it at cheering to you and move on to the next part of the item. But let's applaud you and thank you very much, all of you, for giving us such a delightful half hour. Thank you. Back to you, Diederik, I think.
Thank you so much, Gista. Yes, congratulations from me as well, and from everybody who is watching. I think it is time now for some fun and relaxation. For the last half hour, we will do a pub quiz, and you can win prizes, amazing prizes, or at least fun prizes. Or at least the honor. It's going to be amazing. It's going to be physics related. If you go to www.menti.com, then you fill in this code, and I already see some people doing this with your phone, for instance. So you can use a sort of a second screen to do this, and or you can scan this QR code, and I can already see tens of people gathering, and soon I will cross over to another thing here, and hopefully it all works out, and then we will see we have 30 questions that are going to be about physics, about the NNV, and about the history of physics, and the faster you answer, the more points you'll get, and of course the correcter the answers are, the more points you'll get. It's pretty the same as any quiz, and I am going to stop screen sharing for a moment just to go to I hope that you can see.
Yeah, we can see.
Excellent. Excellent. Great. So all these pictures represent some of you. Most of you are already hopefully signed up at the moment. And we are going to see if it will work. All right.
First question is the enter.
Yes, yes, but I was wondering if everybody is ready. So answer fast to get more points. Physics is called natuurkunde in Dutch. Most European countries use words like fysiek, fysiek, or physic. But who invented the word natuurkunde in Dutch? Was dat Christian Huygens, Simon Stevin, Cornelis Drebbel, of Christophorus Buys-Ballot? So who invented the Dutch word natuurkunde? It wasn't always there. Somebody had to make it up. But who was this? Right